So this is carrying on the series of BGP tutorials. This afternoon I'm going to take a fairly, well, what turns out to be a fairly quick walk through BGP multi-homing techniques. So really much starting at the beginning, but why we want to go and do this, and then giving some examples. So my name is Philip Smith. Work for Cisco, or at least Cisco pay me. I spend a lot of my time walking around, flying around the world, many of the network operations groups, many service provider meetings, registry meetings and so forth, doing this sort of thing, mostly doing workshops. In fact, I've just run here from the IPv6 workshop that Aaron is offering along the corridor. Somehow got roped into doing that as well. So this seems to be most of what I do for my living. So I've been doing the BGP tutorials for NANOG for a year or two or more. And so this is just carrying on that particular series. The presentation slide, pardon me, the presentation slides are, I think they're on the NANOG website now. Well, as far as I'm aware, they should be. If not, you can also get them at the FTP site I've put up there. I mean, that FTP site is actually my personal archive of all the tutorials and presentations and so forth that I've done in recent years. So if there are other things of interest in that particular directory that you want to grab or use or whatever, feel free, help yourself. It is actually a public archive. So ftpeng.cisco.com/bfs/seminars and look for the NANOG 38 presentation. As ever, if you have any questions you'd like to ask, feel free to ask them pretty much any time. The session is actually being recorded, so if you would like to ask a question, please actually come to the microphone and say who you are and ask your questions, just so that we have a record on the archive, on the video recording, just so that the people who view it later on can actually find out what I'm talking about in answer to silence. Okay, the other thing I've done in this presentation is put in a load of configuration examples. I tend to find that doing a lot of these style of presentation, I mean, it's nice and easy to wander through the presentation and not give any configuration examples at all. But quite often I find that people are quite accustomed to a particular command line interface, particular configuration language and so forth. So if you can see the configurations relating to the examples I'm talking about, then it's actually pretty useful. I've used Cisco IOS all my life in this industry pretty much, so that's the CLI I've chosen here. I mean, there's no particular reason otherwise. Hopefully, if you haven't seen Cisco CLI before, that you'll be able to figure out what I'm talking about compared with your favorite router vendor. Tutorial is aimed at service providers, but given that service provider network design and enterprise network design is getting closer and closer these days, a lot of these techniques can apply to to enterprises as well. I'm going to try and go through all these subjects, but why we multi-home, various definitions and options, just so you know what I'm talking about, how we go about preparing the network, looking at some basic multi-homing techniques, going into what I call service provider multi-homing, so it's doing a bit more load balancing, and then the use of BGP communities, which we'll hopefully try and squeeze in before the day finishes. So, why do we multi-home? Well, this is all about redundancy, diversity, and reliability for your actual network. The redundancy part, well, if you've got one connection to the internet, you're pretty much dependent on the router that you're using, the connection that you're using to connect to your service provider, and any of the actual supply infrastructure that goes with that. So if your router decides to expire, or your upstream ISP's got a bad day, or you have an electricity cut, or somebody comes along and digs up the circuit that connects you to your upstream, then, well, you're pretty much disconnected from the network. Now, if you're a part-time player for your internet connectivity, then that probably doesn't matter so much. But businesses these days tend to want to be connected to the internet most of the time, if not all of the time. And so this brings in the issue of redundancy. You don't want to be dependent on one single provider or one single access device or one single WAN connection. So as I was saying, if you're dependent on one router, if you have a router configuration breakage, you could lose your connection. If you have software problems, as can usually happen, you lose your connectivity. You have hardware issues, you lose your connectivity as well. You don't want to be dependent on just the single WAN connection into your premises. It could be physical failure, somebody actually breaks the connection somewhere along the path, or it could be a carrier failure. It could be the telco has some major breakdown in the network and you lose your IP connectivity. You're also dependent on your single upstream service provider. So it could be their configuration, it could be their software, they could be doing any maintenance on the network, it could be the actual hardware, the actual router that you're connecting to. All these can be pretty serious issues. Before I joined Cisco, I mean, I've been with Cisco now for over 8 years, but before I joined Cisco, I used to work for UUNet. I ran the UK network for UUNet's business. We were one of the ISPs that they actually bought up as they expanded out of the US. But when we started in our early days, our main connection from the UK across to the US was a single connection going across to UUNet. And well, it was a usual thing. A US-based ISP would do the maintenance at times that were convenient for them and their customers, which was generally about 4 a.m. to 7 a.m. East Coast time, which of course was not 4 a.m. or 7 a.m. in the UK. It was more like middle of the business day, and it caused us fairly serious upset, especially when customers would phone and start shouting at us. So that brought it home to us very, very quickly that we needed to be independent of other service providers' operational requirements, whether it was doing the maintenance or any other configuration or infrastructure issues that they had. What else? There's reliability. And if you're running business critical applications, then, well, you've got to be available most, if not all of the time. So many sites now are doing e-commerce, so selling products, services, and so forth across the internet. I mean, I can use Cisco as an example, but I mean, many other businesses do the same thing. All of Cisco's orders are now processed through Cisco's website. And if that goes down for any length of time, it means that, well, resellers and partners can't deliver orders and, well, we can't sell product. So that connection has to be on pretty much all the time. Lack of redundancy, pretty much as I said, implies lack of reliability and it implies loss of revenue. The third one is supplier diversity. That's a fairly serious issue as well. I mean, one of the things when we started off in the early days, this was probably in '93, we made a very conscious decision that we're not going to put all our eggs in the British Telecom basket. I mean, British Telecom was the major, almost monopoly telco in the UK. And we thought, well, if we depend on British Telecom for everything, then if they have something seriously going wrong, whether it was customer relationship or in their actual network, then we're pretty much stuffed. And British Telecom, being more or less a monopoly in those days, worked as monopolies do. They didn't particularly care. Customer service was a strange word for them. So we couldn't hope to offer a reliable business, a reliable service for our customers. So we engaged the services of another supplier. So the UK in those days, there were two really. British Telecom was the major, virtually monopoly, and Cable and Wireless, or the local offshoot Mercury, were the second provider. And so we had the two suppliers for our international infrastructure. So we had two circuits across the Atlantic, terminating here in the US, going to different places. One provided by British Telecom, the other one provided by Cable and Wireless. Within the UK, we built a national backbone with circuits from both British Telecom and from Mercury. So even if BT had a major outage, we could still keep our backbone going by virtue of Mercury having their own infrastructure. And that supplier diversity actually paid off big time for us, and more than once, at least in the 5 years that I was involved there. It paid off more than once. we found out in one year, I don't remember which one, that most of British Telecom's circuits went through a town just north of London. Most of the circuits covering the UK backbone went through this town. And they were doing some, I thought, whether it was roadworks or preparing foundations for a new building, but it's the usual famous backhoe incident that seems to populate the NANOG list quite a bit. But somebody had actually dug through the major fibre trunk that went from London to the north, as they called it. And we lost most of our BT circuits that were north of London. It meant we lost about half of our national backbone. But we had the other half still going, because Cable and Wireless, Mercury, did not use any of the BT trunks. Cable and Wireless actually had laid or bought fibre that was laid alongside the railway lines in the UK. And so our backbone kept going. I mean, it made newspaper headlines, it was on the television news, UK internet brought to the knees by, well, excavator, as it's called in the UK, excavator or digger or JCB in Hemel Hempstead. And our MD was quite happy to go on the record saying, yeah, we lost one or two circuits, but we're all fine. We were the only ISP who was able to do that. And that was because we were absolutely pedantic on this supply diversity issue. And if you look at the points I've put there, it's internet connection from 2 or more suppliers, 2 or more diverse WAN paths. We're obsessive with that. Each of our points of presence, we had the 2 telcos coming in there. And it wasn't good enough if Mercury said, oh, we're going to lease a circuit from BT. It was like, no, you're going to go in there with your own connectivity, which quite often meant they came in with microwave rather than fibre because BT had the entire fibre access. 2 or more exit points, 2 or more international connections. We had an international connection from Cambridge in the UK and London in the UK to go over to the US. We landed in Washington, we landed in New York. And that gave us very, very big diversity there. I mean, I can tell more stories about problems with that. You know, Mercury doing maintenance on the transatlantic cable moved us temporarily onto a BT circuit, and guess what happened? The BT circuit failed, and then Mercury had forgotten to move us back to their original one. And so we lost both transatlantic cables, or connections. Anyway, the point I'm making is it's 2 of everything. And we were quite obsessive about having 2 of everything. We were the only ISP who actually did that. And many of our competitors were a lot cheaper than us. But we were the only ones who could actually guarantee the 99.5% availability that we claimed for our network. And this is back in 1994. I mean, people couldn't even offer 90% availability back then, and we were doing about 99.8, 99.9 back then. Even with sort of the lazy software and hardware they had in those days, that was all quite possible because of the diversity thing. Okay, this isn't really a reason, but when you talk to people about why they have got 2 connections to the internet, they say, oh, well, we use it to play one of our providers off against the other one, 2 ISPs. So for service quality, service offerings, availability, and actually price is the 4th one I should put up there. It's quite often you find, especially in parts of Asia, ISPs will get a connection and they pay so much for it per month, and then they start shopping around, or they maybe come to some of the operations meetings and find out that another provider does something cheaper. So they go back to the original supplier and say, hey, I can get a connection from X for this much. Can you match it? And they often do, without any question. So you find that you get a lot of situations where it's purely for playing one ISP off against the other one. I mean, I wouldn't use that as a justification for multi-homing, but you quite often find it as a reaction, or one of the side effects. So it's very easy for the company board to come along and say, yeah, we've seen all this. We need to multi-home because it's good. It gives us reliability for our business, redundancy, and so forth. Go and do it. It must be very easy. Just go and look up a web page somewhere and type into your commands, into your router commands, so that it will just automatically and automagically do multi-homing. And the way it is presented, quite often I see it like that. It's like, oh yeah, we're going to multi-home. There must be a command to do that in my Juniper box or my Cisco box. There isn't really. And usually the poor network engineer is faced with this task that his bosses think will take 5 minutes, and actually it takes really the rest of the lifetime to try and keep the whole thing going. So what does it actually mean? What do we have to do? What does it actually mean for the internet and for your own network? So I'm going to look at some of the definitions and options now. So it's really, what does it all mean? What do we need to do? And what happens? Well, my multi-homing definition is actually fairly straightforward. I suppose if you ask on a mailing list, or if you have a look at some more official documents, what does multi-homing mean, you can end up with a very large document giving an explanation. But for me, at least from the technical point of view, it's basically you've got more than one link external to the local network. So it could be 2 or more links to the same ISP, or it could be 2 or more links to different ISPs. And that's pretty much all it is. Usually 2 external-facing routers. And I'm always a little bit disappointed when people come along and say, oh yeah, I'm going to multi-home, but I'm only going to use one router. And it's like, well, yeah, sure, you can multi-home, but you've lost one really important aspect. You're dependent on that one box that you have. And you know, your vendor will come along and say, yeah, but my box, 100% reliability, I can guarantee that. Well, their guarantee is, it's a marketing guarantee, you know, because they never think that you'll actually come and follow up with the loss of service that you've had. And they just bank on that. So they say, yeah, 100% guarantee, no problem. But in reality, you're going to have to upgrade software at some stage. You're going to have to do maintenance on the router at some stage if you move it from a different rack and all this type of thing. So having one router doesn't really make a lot of sense. So all the examples I'm going to show here assume 2 external-facing routers. That's really important. The second thing, well, we're going to use BGP. And certainly if you're going to use BGP connecting to another service provider, you're going to need a public AS number. So an AS number is autonomous system number required by BGP. You obtain that from an upstream ISP who is a member of a regional internet registry, or you get it from the regional internet registry yourself. There are 5 of the regional internet registries. For you, ARIN is the registry that you probably go and chase after for an AS number. If you're a member of a registry, which I really strongly encourage, then it's very, very straightforward procedure to get that. If you give them the AS numbers of the 2 ISPs you're going to connect to, you get your AS number. AS number is a 16-bit integer, ranges from 1 to 65534. The first and the last one are reserved. And there are 1,023 private AS numbers. The private AS numbers are meant for use within your own network. They're not meant to be visible on the public internet. So it's a bit like private address space. Private address space is not visible on the public internet. It's intended for use on private networks that aren't connecting to the internet. Where you would use a private AS number, well, typical application could be an ISP with customers multi-homed onto their backbone. So RFC 2270 actually describes how Internet MCI did their customers multi-homing onto their backbone. So that's actually quite a nice informational document that explained what they did. Or it could be a corporate network with several regions, but connections to the internet only in the core. So head office connects to the internet, and then the corporate network will connect into the headquarters. So something like I've drawn on the slide there. So you have the regional offices around here, headquarters there, and the only connection is out to the internet at headquarters. The idea behind splitting it up like this is you can give each regional office their own autonomy. So you as the administrator of the network don't have to go to some different state or different country or whatever to actually administer the networks there. You can give those guys their own their independence. Another thing is within a BGP confederation. BGP confederation is one technique for scaling BGP. If you came to the last NANOG, well, you would have not seen me talk about BGP confederations, although the slides were in the actual presentation. But if you want to check what a confederation is, then have a look at the NANOG 37 slides. There are about a dozen slides there describing what it is. Now, I said that the private AS should not appear on the public internet, so it's actually good practice these days to remove the private AS from any prefixes that you're going to announce to the internet. So what to do is just include a configuration in your configuration template, just a line that says strip out the private AS numbers. So the iOS example would be this on the neighbor statement, just a neighbor remove private AS. If you go to the Project Gumri website, you'll actually see configuration examples for well, the major router vendors and how to strip out the private ASs. I mean, in saying that, I don't know if you know, but one of the things I do in my, well, spare time or whatever it's called, is produce this weekly routing table report that goes to the NANOG mailing list amongst many other mailing lists. And if any of you watch that, you'll see that there are private AS numbers appearing on that from time to time. So not every ISP actually follows the best practice of stripping out the private AS numbers. But it is actually considered today to be a best practice. Now, with configuring policy, I mean, this is Cisco specific, but for configuring policy, all router vendors produce weird and wonderful configuration languages and many different ways of doing the same thing, and it's very easy for the newer ISP to get completely lost. It's actually very easy for even the experienced ISPs to get completely lost, because you can actually do many of the same things using different techniques. So the purposes of this presentation, I want to try and keep things simple. Everything in life should be simple, I think. So if we try and keep the configuration simple, then there's actually less to go wrong. So in all my examples, I'm going to use prefix lists to filter prefixes, filter lists to filter based on AS paths, and route maps, the iOS route maps to apply the policy. You can filter ASs and prefixes within route maps as well, but it just increases the chances of something going wrong. So the policy tools, well, within BGP, we've got the local preference attribute. If you apply local preference onto a BGP peering, it is of use for inbound routing announcements. If somebody announces you a prefix, you can attach a local preference to that prefix to indicate the outbound path in your network. Remember, highest local preference wins. So local preference is used for controlling outbound traffic flows in your network. I mean, it's simple for me. I took what, 30 seconds to say that, but it's amazing that this is the thing that trips up most people when they try and implement multi-homing at any stage in their career. They just forget, and they end up using other weird and wonderful techniques that their favorite vendor has conveniently provided on the router. Local preference lets you manipulate outbound traffic flows. MED works in the opposite direction. It lets you manipulate inbound traffic flows between you and your neighboring AS if you're multi-home to that AS. It has no impact on an internet-wide scale, but it's useful if you've got more than a single link to your neighboring autonomous system. So that's why I've called it local scope. The AS path prepend is for inbound traffic flows, but it has an internet scope. What an AS path prepend is, on your outbound routing announcement, you will change the apparent length of the AS path. So you make it look longer than it really is. You can't make it shorter than it really is. Although never a month goes by, certainly on our Cisco BGP list, coming from a customer who wants us to put in a command to strip out ASs in the AS path, which would definitely be not a good thing to do. So AS path prepend will artificially lengthen the AS path, and that actually is visible across the entire internet. When you can go onto many of the looking glasses around the world and you see the effect of the AS path prepend coming from really remote locations. The final policy tool you have is the BGP community. BGP community is not a collection of happy routers, but it's actually a collection of prefixes that have the same policy. The reason I said that is that when I do workshops, I put a little quiz at the end of the week to see what people have learned. And the amount of people who answer that as a collection of routers talking BGP is actually quite funny. But communities, it's for specific inter-provider peering. Communities are used a lot for ISPs doing load balancing within a small group of ASs. And it's right at the end of the presentation, I'll show you some examples of service provider-based communities. Okay. Originating prefixes. This is an interesting one. for many of us who've been in the industry far too long, this has been obvious. It's like you get your address block from the registry, so whatever it is, /21 today, you get your address block and you announce it to the internet. I mean, what else do you do? But a lot of newcomers to the internet seem to think, well, you get your address block from the registry, but you only announce the IP addresses that you're using. And so certainly in the part of the world that I come from, you see ISPs, each /24 they use, they start announcing to the internet. So out of a /21, you end up with, well, 8 /24s appearing, which is not actually quite the way to make any of this work. And then I get a panic email 6 months later saying, oh, wow, we're trying to multi-home, and it's really complicated because they're announcing all these /24s. And when asked the question of, well, why are you announcing all these /24s? The answer is always, well, what else are you meant to do? The assumption from when you get an address block from the registry, the assumption is that you announce that address block. It's an address block. In the old days, before 1994, you got Class Cs and Class Bs and Class As. It seems that certainly many university systems and other educational establishments still teach the classful routing system, where you could only announce /24s or /16s or /8s. So many people still think that way. Whereas the assumption these days, since 1994, has been to announce the address block that was assigned by the registry. So the current registry minimum allocation is a /21. Well, Afrinic and LACNIC, it's a /22, I think. Actually, several ISPs filter the registry blocks on this boundary. The registries actually publish their minimum allocations. I've got that on the next slide. And ISPs will filter on that boundary. So if you announce a /24 without announcing the covering aggregate, you have no connectivity within those ISPs. Several ISPs filter the rest of the address system, sorry, the rest of the address space according to the IANA assignments. So they say, well, IANA only ever handed out /16s or Class Bs out of 128 to 191, so we're going to filter on /16. So if you take this /16 and chop it into pieces, you'll get no connectivity there either. So that's what some people have called the net police activity. And there's no such thing as a net police, but it's got that name over the years. So there are the registries. They publish the minimum allocation sizes. Those URLs were correct the last time I looked. Hopefully they haven't changed, but that's basically what each registry does. IANA publishes the address space it has assigned to NSITE and to the RIRs, so that is listed here. They haven't published the /16 announcements, but sorry, the 16 assignments, but they've published the /8 assignments. Several ISPs will use this published information to filter the prefix announcements. So that's just one thing to watch. I mean, the whole idea behind the net police was to punish ISPs who pollute the routing table with specifics rather than announcing aggregates. I mean, I think that made a fair amount of sense when the internet was basically the US, Canada, and Western Europe. So in the mid-90s, early mid-90s. But now it makes less sense because the Asian internet is growing very, very fast. The African internet is growing quickly as well. Latin American internet likewise. And those guys have got much greater infrastructure challenges than we have. And actually, this filtering makes a lot of the multi-homing really difficult for them. I've been involved in many cases, especially in South Asia, where these filters have caused problems for people trying to multi-home. Also, it is hard to maintain. I've got time for another story? Yes. I was in Mongolia, was it last year? I think it was last year. And I was doing a BGP multi-homing workshop there. And so I turned up with a colleague from Nepal, and we were doing the workshop. And some of the ISPs started asking questions. Mongolia is interesting because they can only get transit two ways. One way is through China, the other way is through Russia. Or they can go by satellite, which is too expensive. And they were having problems accessing a lot of internet sites. And they reckoned they were either having problems with the Great Firewall of China or with the unreliability of the Trans-Siberian Railway. Because the main fiber that goes to the east of Russia apparently goes along the Trans-Siberian. So they just put it down to, well, you know, unreliable infrastructure and the Chinese filtering. So I said, well, let me have a look at the router. I'm just curious to see this because I didn't think that the Chinese were actually filtering transit. So I had a look. And so I asked the question, well, when was the last time that this configuration was updated? Oh, some consultant came from the US 6 years ago and he set it up and told us not to touch it because it would break. So we haven't touched it. Guess what he had put on? He'd basically taken the IANA assignments and put filters in to basically block anything that was not assigned by IANA in 1999. Look back at the routing table, or at least the IANA assignments for 1999, and see what was missing. They basically cut the Mongolians off from about 3/4 of the internet. I got rid of the filters, and guess what? It all magically worked. So this is a big word of warning. If you're going to try and do this sort of filtering, keep it up to date. In fact, Rob Thomas has been very, very aware of this issue, and the Project Gumri guys are really good. They've actually offered this BGP feed for free that will give you the current Bogon prefixes. And you can just, the URL there just describes what you've got to do, how to go and get one. It describes how you configure it in your network. It's just a sort of remote triggered black hole type configuration. They send you the current prefixes that are considered Bogon, not meant to be routed on the internet, and you can use that to ensure that no garbage ends up on your network. That's the best way to do it, rather than putting in static filters that you then get a better job offer from and head off to your sunny climes, leaving whoever replaces you, who probably doesn't know anything, to, well, try and figure out what you've done or not, as in the case of the Mongolians. Okay, so that's a word of warning with trying to do any of this static fixed filtering. It could come back to bite you later on. I mean, actually, we see this issue every single time the registries want to start using IP addresses from a new address block. I mean, when I was in Nairobi for AFNOG, we spent our time chasing around Italy and bits of the US trying to get connectivity for Network 41, because the African ISPs who were trying to use it ended up being black-holed in various parts of the net. Okay, looking at some multi-homing scenarios, we've got, well, stub network I want to look at, multi-home stub network, and going through to the real multi-home network and load balancing. So if you've got a situation like this, which is just a stub network, your router is there, you've got parallel connections to your upstream provider, it lands on the same router on your upstream provider. There's no need for BGP for this. You can run BGP if you want. I mean, if you want to go play, you can run BGP, but there's no need. Certainly if you turn up at a registry and say, hey, I want to get an AS number because I'm multi-homing to my upstream, they'll say, no. Okay? So all you do here is actually point a static default route to your upstream. The routers will quite happily load balance. And your upstream will just point a static route on the two links for your address space back to you. And that's all you need to do. It's just as though you had a single statically connected connection. All that this will give you is circuit or WAN redundancy. It doesn't give you router redundancy. It doesn't give you upstream infrastructure redundancy. This one gives you upstream infrastructure redundancy. You may be connecting to different routers in the upstream or different points of presence. Okay, so in this case, you would use BGP. But then again, I see far too many people trying to use OSPF or RIP or something worse to try and handle this. An interior routing protocol, well, interior means inside. It doesn't mean outside. But people still try and use OSPF for this sort of thing. So between these two different networks, run BGP. It's the easiest way of trying to do this. Use a private AS number, as I've done there. So a private AS is used for this. Talk to your upstream ISP. He may just assign you a private AS number, or you can make one up for yourself. And use that, and you just configure it as with BGP as normal. This one, well, many situations are possible here. This is the true multi-homing. AS100 has got two links to 200. And you maybe uses AS300 as a backup or something like that. You've got to try and figure this out. You've got load balancing on between 100 and 200, and you've got load balancing between 200 and 300. It gets a little bit more complicated. But the thing is, so many people come up to this and they go, oh my gosh, complicated, complicated. What should I do? And this is where they tend to go to pieces. And the whole point of this presentation is really to take this situation and explain the simple logical steps you can take to making all this work properly. But before we do that, let's look at some cases. You've got multiple sessions to an ISP, maybe something like this. You can actually use BGP if you want to. So rather than having static connections, you can use BGP with whatever AS numbers are required here. Use something called eBGP multi-hop. Now, you can run BGP on each individual link, but that starts getting a little bit ponderous. You can actually instead run BGP between the loopback interfaces in each autonomous system. Right? What you do then is, so you run the eBGP to the remote loopback, and then you point a static route for the remote loopback onto each of the serial interfaces that this connects to. And what the router will do is basically use each serial connection for any outbound traffic. You need to make one change, eBGP multi-hop 2. eBGP by default assumes that the time to live is 1. Okay? This says we're going to change the time to live to 2, so the BGP can be up to 2 hops away. Sorry, the BGP neighbor can be up to 2 hops away. And that allows the eBGP to run between the loopback interfaces. One caveat with eBGP multi-hop, I should state up front that I really don't like eBGP multi-hop at all. Probably because I've been an ISP and I've had endless problems with customers trying to use it and breakages in networks and customer blaming us for what's basically their mistake. One issue is this. If you've got a eBGP multi-hop session running along here between R1 and R3, well, you're obviously going to configure it with eBGP multi-hop 2 to have it run between the loopbacks. But this is also a valid path. So if this link breaks, you get a backup this way. And that also will work with an eBGP multi-hop 2 because it's 2 hops away. And, well, this has been the major issue that we've always run into. Customers have gone for weeks and weeks without realizing that one of the links is down. And then they just notice, oh, the network's got a bit slow. Oh, well, there's something wrong with my ISP. They're just being useless or something. So after about 2 months of frustration, they start screaming at the salesperson, saying, what's wrong with your network? It's been really bad for the last 2 months. And then, well, we go and have a look at it. And it's like, well, one of the links been down for the last 2 months. Oh, well, we don't know, but that's, and so on. So you get that. So that's one thing you've really got to watch. It's an extra load that the upstream service provider has to be aware of. So I always say try and avoid using it unless it's absolutely necessary, there's no alternative, or you're trying to do load sharing across multiple links. In fact, most times you see eBGP multi-hop used is for providing a BGP feed for some of the BGP information services, or if you're signing up to Rob Thomas's Bogon feed, and so forth. I got this from one of the bigger ISPs here. We said, well, what do you guys do for eBGP multi-hop? And they said this, almost word for word. We will run eBGP multi-hop, but do not support as a standard offering because customers have a hard time managing it due to routing loops and failure to understand that session stability problems can be caused between their border router and wherever the eBGP lands within their own network. And the customer ends up blaming the upstream ISP for basically something that goes wrong with in their own network. When I say all that, but I still find something through parts of Asia that this seems to be the favored way. ISPs have got one router in the middle of the network that all the ISPs, the customers, talk BGP to. And, well, those poor customers seem to have endless problems all the time because of the single point of failure of this one particular router. So try not to do it. This one's gone completely out of favor these days. It seemed to be a really nice idea at the time, and this is this BGP multipath. What happens here is the router will put multiple paths into the forwarding table. You end up running 3 BGP sessions in this example of 3 links. You run 3 BGP sessions between the autonomous systems, which seems a nice idea. Bear in mind that the internet routing table, well, this morning was 199,780 prefixes. So you're basically ending up with almost 600,000 paths on the router in, say, AS300. That takes quite a bit of memory, and it takes quite a lot of CPU to actually process all those paths. So it's really a fairly significant resource burden. So you find that people tend not to do this anymore these days, unless it's a simple situation. But just to let you know, it exists. Something like this, well, for any generic multi-homing like this, I mean, this would be my ideal way of trying to multi-home, say, between you and your neighboring AS. Use separate routers, different circuits, go to the separate routers in the upstream, separate points of presence if you can do that. The simplest scheme is always to rely on the defaults. And some people try and go really, really complicated all from day one, whereas actually it's much easier just rely on the defaults and then just leak selected prefixes to give yourself more control. Unfortunately, that actually needs a little bit of planning and a little bit of work to make it happen. So you point default route towards one ISP, generally what people do, learn selected prefixes from another ISP, and just modify this number of prefixes until you get the acceptable load sharing. There's certainly no router BGP multi-homing command on any platform that I'm aware of. So you have to be prepared to sit down and do a little bit of work. The idea behind the presentation is to give you enough tools to be able to sit down and do this work. Okay, so preparing the network. Well, the first thing we do, we're trying to put our own house in order, so we're going to deploy BGP across the network before we try multi-home. We need an AS number. If we're going to multi-home to different ISPs, then we need a public AS number. So you either go to the upstream ISP, who is a member of a registry, which is fine. You can get one from them, but bear in mind, if you do that, the AS number is still their one. So if you decide to change an ISP, you've got to hand back your AS number. Apply to the registry yourself for a one-off assignment. I don't know if Aaron supports that, but certainly some of the other registries will do that. Ask an ISP who is a registry member, any old ISP. That can usually work as well. You can become a customer of them. Or, in fact, the best option is to join the registry yourself and get your own IP address allocation. Multi-homing with other people's address space is hard. Okay? I mean, technically it is simple, but for every other reason, operationally, it's actually quite difficult. Most ISPs don't like anybody else announcing their address space within anywhere else on the internet. So trying to multi-home with other people's address space is actually pretty difficult. So if you're going to go down the multi-homing path, it's best to get your own address space. I'm not up to date with Aaron policies, but certainly APNIC has a multi-homing policy. If you're an organization, any old organization who wants to multi-home, you will get an AS number and an address block just to let you multi-home. And that one certainly has solved a lot of problems with small organizations who are trying to multi-home with 2/28s and then can't work out why they don't get any connectivity whatsoever. Okay? So I strongly recommend the final option there. Join the registry, get your own address block. So we're going to look at just one example. Network is not running any BGP at the moment. This sort of represents a standard small organization. I mean, I know I'm talking to you mostly as ISPs who are probably running BGP to some extent already. But if you've got customers coming along who want to multi-home, this is sort of the steps you've got to go through to prepare them to multi-home onto your backbone or between you and another provider. So we're not running BGP, we're not running any IGP either. So we want to pick our interior routing protocol, OSPF or ISIS. The choice is yours, whatever you're happy with. Don't send an email to the NANOG list saying, hey, which IGP should I use, OSPF or ISIS? Because you get all the OSPF fans saying, OSPF is the best. And you get all the ISIS fans saying the same thing. And then you end up with lots and lots of discussion on NANOG, which actually might end up being technical discussion, which would be a nice change. I didn't say that, sorry. Assign loopback interfaces and a /32 address to each router, which will run the IGP. Certainly in iOS, the loopback is used for OSPF and the BGP router ID anchor. And it's also used for iBGP, it's used for router origination and so forth. So that's quite nice. Deploy OSPF. I mean, that's easy, actually. People think, oh, deploy OSPF, it's going to completely break the network. But it doesn't. If your current network is all static routes, Static route, certainly on a Cisco box, has a distance of 1. It's the highest protocol distance apart from being connected. Protocol distance of 1. OSPF has protocol distance of 110. It is less important. So if a prefix pops up in OSPF and is known by a static route, guess who wins? The static route. People don't believe me when I say this, and I've walked into so many networks, deployed OSPF, and people say, gee, the network still works. And it's like, well, what did you expect? Okay? And it's because of this, smallest distance wins. So you can deploy OSPF on an existing, working, operational, statically routed network with no problems. Just some general recommendations. Be prudent when deploying the IGP, so keep the link state database lean. The whole design goal about deploying OSPF is to minimize the number of prefixes. The fewer the prefixes, the faster the convergence. The faster the convergence, the faster you work around failures within your own backbone. If you've got a few prefixes within OSPF, you can tune the timers. I mean, certainly Cisco timers are very generous. A lot of ISPs are now tuning these timers to give themselves maybe 1 or 2 or 3 seconds failover time, and it works fine. So the router loopbacks will go into the IGP, WAN point-to-point links within the backbone go into IGP. In fact, any link that has a dynamic routing protocol running on it should go into the IGP. Everything else, and I mean absolutely everything else, goes into your internal BGP. Then IBGP is the load carrier. You put all the junk in there, keep IGP a lean and mean protocol. So things that don't go into OSPF could include dynamic assignment pools, so DSL, cable, dial, wireless, customer point-to-point link addressing. If you're monitoring the links to your customers, don't put those links into OSPF, because every customer you have is one entry in the link state database. 20,000 customers later, you have a very big and scary IGP. So customer point-to-point link addressing, put that into BGP. Or if you don't monitor your customer connections, use next hop self instead. What next hop self does in IBGP is change the external next hop to just being your local routers, your aggregation router. So you don't need to carry the external point-to-point links. Static or hosting LANs. If you've got, say, hosting services, don't put those LANs into IGP. There's no point. Put those into BGP, your customer address space. Likewise, address space that you give to remote customers, put those into BGP. In fact, anything that I didn't list in the previous slide. If you can count the routers in your backbone, that's pretty much the ultimate goal of the number of entries you should have in your IGP. So some of the biggest ISPs, who've got thousands of routers, actually have very small IGPs. Yet I walk into very small ISPs in some parts of the world, and they've got massive IGPs, 16,000 prefixes in OSPF. And they're whinging about, oh, well, your product is really, really bad, you know, it's so slow. And it's like, well, if you design it badly, what do you expect? This is what you should be doing. Throw all this stuff out of OSPF, and then it'll work. I've got another story about that, but I'm running late, so I won't tell you. But it's along those lines, you know, people laughing at my recommendation, then 6 months later coming back and saying, oh, yeah, maybe you were right. Anyway, so introducing OSPF. So I've got, put the loopback interface there, /32, my Ethernet for the backbone, my serial interfaces where my customers connect. So I've got the loopback into OSPF, I've got just the network carrying, so the backbone links, I mean, what is it? I don't know what I'm doing here. What's this? 121.10.2.0, yeah, sorry, that's the Ethernet, the backbone for the POP. Everything else is not talking OSPF out there. The only interfaces we're talking out is Ethernet. We've got the static routes for the customer connections here. These will go into BGP. So that's pretty much how we introduce OSPF. Now, what about preparing the network for IBGP? Well, for a long time I just said, just run IBGP everywhere. And then people started asking questions, well, but why? And the answer of, well, why not, wasn't good enough. So I put in a few slides to explain why, the whys and wherefores of running IBGP. You can run IBGP on all routers, which is my favorite one. There's absolutely no reason why you can't run IBGP on everything. And there's still people out there who seem to think that any router that doesn't occupy half a rack can't run BGP. Whereas in fact, well, the V6 workshop along there where you're running iBGP on routers little, well, but half the size of my laptop. Or you can run iBGP on a subset of routers, which subset, or just an upstream edge. But the important thing is to run iBGP on all routers which are on the transit path between external connections. If, for example, the link between A and B breaks, your backup path is going to be around like that. If D and C have no idea how to see all the external part of the network, then you end up black holing outbound traffic or inbound traffic. So you've got to watch that. So transit path is the important one. So in this case, only A, D, and B need to run iBGP, whereas in the previous example, all the routers in that network needed to run iBGP. So for C, E, and F, static routes or just simply relying on the IGP is sufficient. Okay. Now, second point, typical service provider networks have 3 layers. The core is generally the backbone, so that's the transit path. Anything is a transit path people refer to as the core. The distribution layer is basically the middle of the network. Some ISPs don't have this, the smaller networks tend not to. That's the POP aggregation layer, where you would take regional or local POPs and aggregate them into the core of the network. And then the aggregation is, well, the remote points of presence where the customers are actually connecting to the backbone. Now, at the aggregation layer, we start at the outside edge. iBGP is optional. Many ISPs actually run iBGP here, either as partial routing, which is most common, or full routing, which is less common. By full routing, I mean these routers at the edge of the network see the full internet routing table. By partial routing, I mean these routers will only see the prefixes originated by the local AS. Okay, they're not going to see any prefixes from outside the autonomous system. Okay, full routing is not needed really unless customers want the full table, and I generally don't really like giving customers the full table because it's expensive to do. Partial routing is much cheaper, much easier. Network convergence is much quicker. It's not so much a memory burden or CPU burden. And communities and things like peer groups and iOS make this administratively very simple to do. I hear reasons like many aggregation devices still can't run BGP. And I think that's getting less and less common these days, but there's still some out there. Certainly in the old days of big dial aggregation networks, I mean, none of these dial boxes could run BGP at all. You got RIP if you're lucky, and that was it. So what you do in that case, you have static routes from distribution devices for address pools. Use the IGP for the best exit. Distribution layer pretty much always runs iBGP. Some people try and miss it out. But if you do that, then you've got to start using IGP or relying on your static routes again. And relying on static routes gets a little bit harder. If you use the IGP, then it doesn't scale because you have to start putting customer prefixes into your IGP. So you're breaking the whole point of having a nice, tight, scalable network. Networks which plan to grow large should deploy iBGP from day one. I mean, I know it sounds a little bit funny to say that, but when I present it like this, people say, what, you mean there's some networks that don't plan to grow large? Well, clearly, because they seem to think that they only need to run BGP on one device in the network, and they're quite happy to come and redesign it 3 years' time when, ooh, we need to do something different. There's absolutely no overhead in deploying iBGP. I mean, all the ISPs I've been involved in setting up to some extent or other, we set them up running full iBGP, using route reflectors for scalability, even though I've only got 3 or 4 routers. We set that up from day one. And, well, the first one I ever did was 7 years ago, and they're still doing. The configurations are exactly the same as they were 7 years ago. They have not had to touch the iBGP configuration. They have just added more routers as the network has grown. And that's the ideal way. It's the best way. They'd be able to concentrate on other things about scaling the network. The core of the network is usually the transit path. iBGP, of course, is necessary here, full routes or partial routes. If you're a transit provider, so providing transit for other autonomous systems to the internet, then you tend to need to carry full routes. I mean, you can try and do it in partial, but it gets a little bit hairy to try and manage it properly. Whereas if you're sitting at the edge of the internet, you're not really a transit provider for multiple ASs, you can get away with just carrying partial routes in the core. So what you have to do is decide on your best IBGP policy. Is it full routes everywhere, or partial, or some mix? Figure out your scaling technique. So what community policy are you going to use? I know I haven't really talked about communities here yet, but I have done before. Are you going to use route reflectors? I tend to say yes. Start with route reflectors from day one. People don't deploy BGP confederations in new networks anymore these days. Route reflectors are much simpler. And any other shorthands or configuration shorthands that your favorite vendors introduced. So for example, in Cisco's case, peer groups, peer templates, and so on, just to make it easy. And then you deploy IBGP. Step 1, introduce IBGP mesh on the chosen routers. Yes, you can do this without breaking anything in your backbone. Amazing but true, because the IBGP distance is greater than the IGP distance, or the static route distance. In iOS, the IBGP distance is 200. 200 is a lot bigger than 110, which is a lot bigger than 1 for the static routes. So you can deploy IBGP across your entire backbone, and nothing will happen apart from IBGP running. You put the customer prefix into IBGP, well, everything should still just work. Because if you already got static routes doing that job, there'll be no difference. The static routes will still override the IBGP entries. The big one is step 3. Carefully remove the static routing for the prefixes now in IGP and IBGP. So there you've got to do the check, does the network still work? You don't do what some people have done. It's like, yeah, I've done it all now, and you run around all the routers ripping out static routes. Pick on one router, preferably with a friendly customer. I mean, I don't know how your networks are set up, but I mean, generally pick on the router that your staff connect to. So when they go home in the evening and it doesn't work, you get them back into the office. And of course, they do some more work, but at least you know you can fix any of the problems that are there. Pick on friendly customers, and then once you're happy with that, content with the migration, then you can move to the next router and so on through the network. What do I mean by install customer prefix into IBGP? Well, that's the customer assigned address space. So certainly in iOS case, it's a network statement for BGP, static route pointing towards the customer interface. I don't know, in my case, I would generally use a unique community to identify customer assignments because I use communities a lot. So I use communities for customer assignments, I use communities for hosting sites and infrastructure and so forth. Customer-facing point-to-point links, put those into the IBGP as well. If you're going to monitor customer connections, put them into IBGP. Yes, I know you end up with a lot of /30s in your IBGP, but who cares? I start caring when I see people announcing /30s out onto the internet. But IBGP, being radical here, is different routing protocol from eBGP. eBGP is what you use to talk to other people. IBGP is what your routers use to talk to each other inside your network. So you can put basically any old thing into your IBGP. So put your customer point-to-point links in there. Use a unique community for those as well to identify them. So maybe you only announce those prefixes to the part of your network that hosts your monitoring system. That's a nice, tidy way of doing it. Dynamic assignment pools, local LANs, all this sort of thing. Put those into your IBGP. Carefully remove static routes. As I was saying, do one router at a time. Pick on a friendly customer, preferably your staff, if you provide staff with connectivity. So you remove the static route. Does it still work? If it doesn't work, put it back and figure out what went wrong. Oh yes, remember to look in the routing table, in the RIB, not in the forwarding table. Okay, that's pretty important, because the forwarding table will have the result. Okay, so the result, you need to know how the result got there. Did a static route put it in there, or did OSPF put it there, or did BGP put it there? Okay, so look in the RIB. And then move on to the next route until the whole POP is done. Then have a break, wait a week or two, and then go on to the next point of presence. So come up with a nice methodical plan for doing the migration. I mean, I've done this many, many times, and I make it sound gloriously simple, but when you do this the first time, it's a little bit, well, intriguing. So previous steps are not flag-based steps. In fact, you can just do this on successive maintenance periods, or maybe each step per week. That works quite nicely as well. Okay, and if you do it properly, plan it properly, customers will not notice. Okay, I mean, I'm not suggesting at all that you do this on a live network, but the impact of this is such that you can almost do this on a live network and nobody would notice. Okay, so rather pick your maintenance period and do it during that. So now you've got the IGP essential networks in IGP, you've got customer networks in IBGP, it's deployed over the backbone. BGP distance is greater than any IGP, which is what you want. So you're now ready to deploy external BGP. And as I was saying before, external BGP is a different thing altogether. It's different protocols shared by the same name. So we're now going to look at the basic multi-homing part, and hopefully I can do this. When's the break? 1:32, yeah, 3 o'clock. So 20 minutes left, so we should try and get through most of this by 3. This is basic multi-homing. So we're going to assume that you're sitting right at the edge of the network. So you don't particularly care about outbound traffic flows. You're only really trying to worry about how traffic gets in to your network. So I've called it no-frills multi-homing. We're going to look at 2 cases, well, only 2 cases to look at, multi-homing to the same ISP and multi-homing to different ISPs. I'm going to keep these examples very simple, because if I can keep them simple, then you figure out how these work, it becomes very easy to add to them to make them a little bit more complicated. In all these examples, I'm going to assume that the site has a /19 address block. There's no reason for a 19 apart from, well, when I first wrote those slides, the registry's minimum allocation was a /19. So we've moved on a little bit from that now, and there's no real reason to change. It works for any address block size that you have. So this is most commonplace at the edge of the internet, as I was saying. So if you're right at the edge, here the networks are usually concerned with inbound traffic flows. Outbound traffic going by nearest exit is usually sufficient. Okay, nearest exit routing is usually sufficient because an edge ISP will have probably about 60 or 70% of the traffic volume coming in versus about 30, 40% going out. Well, at least that's sort of what it was. I mean, it used to be about 70-30. I've seen it 80-20 in some parts of the world. And of course, BitTorrent and other peer-to-peer friends have kind of changed the balance quite substantially. And there's some ISPs in the last few months I was looking at, I was seeing 50-50, which is actually a bit freaky because these people were actually at the edge of the internet. But they just had a large number of broadband customers who left their PCs on all day, all night, and were happily serving up content to the BitTorrent world. But assuming simplicity, we're not going to care about outbound traffic, we're only going to care about inbound. So looking at multi-homing to the same ISP, well, for this we're going to use BGP, surprise, surprise. We're going to use a private AS number. So a private AS number is 64512 and above. Which number do you pick? Generally, your upstream ISP will tell you which one to use. They may have a scheme for all their customers that multi-home onto their backbone. Okay, they may have picked one AS number that they use for that. In fact, I think 1 or 2 ISPs actually use a public AS number for this type of multi-homing as well. Last time I looked, I think it was UNet certainly did this, and I'm sure others, I've heard that others do too. But there's no need or justification for in this case, for the provider to, or the ISP to have a public AS number. You won't get one from the registry. The nets from this end site being visible on the internet makes no sense. The address space comes from the upstream provider's address block anyway. They're going to announce their aggregate. So announcing the sub-prefix of the aggregate gives no extra benefit at all. Okay, so the first example we're going to look at is one link being the primary path, the other one being the backup path. And this applies when the end site has bought a large primary WAN link to their upstream provider and a small secondary as a backup. So it could be, well, in euro bandwidth, it could be an E1, backup could be 64. I know it doesn't make a lot of sense to have something like that, but I'm just trying to use this as an example. This was actually one of the services that our dear friendly salespeople back in my early days came up with. Oh yeah, great service to have. So we went and deployed it, E1 primary, 64K backup. When the E1 went down, They couldn't actually explain to me how an E1's worth of traffic would fit in a 64K link. Somehow they thought there was some magic that would make this work. But it's actually a useful example to show a primary backup, because it's a good educational tool, even though you probably never use it in reality. So you've got your AS65534. That's just the one I chose for here. We've got primary path between router A and router C. We've got the backup path from B to D. We're going to AS100. Router E is the border router for AS100, and he will strip out the private AS and just announce the 65534 address space as part of AS100 address block. So that's the picture. So what are we doing? Whoops. So we're going to announce a /19 aggregate on each link. Okay? Remember what I said away at the beginning? When you get an address block from the registry or whoever you get it from, announce it as that. It's an address block. That's what you announce to the internet. On the primary link, you announce the /19. On the backup link, you announce your /19. It means that if one link breaks, because you announce the /19 on the other link, it basically all the inbound traffic will use that instead. That's the whole idea. I mean, people I've seen have come up with some wonderful multi-homing schemes, but they forget about the fundamental. What happens if one link goes down? Because they forget to announce the aggregate. So that's pretty important. You find all my examples start off with the same first line. Announce a /19 aggregate on each link. So what we're going to do, primary link, announce the 19. Inbound, we receive just the default route. Again, a favorite on international ISP scene is, oh, multi-homing? Oh, you need full internet routing table from us, because that's the only way you can do it. Really? Well, I've been involved in many cases trying to arbitrate there, and, well, it's quite interesting. Whoops, it's quite interesting, because the upstream ISP says, oh, you need this brand of router with this much memory and this much CPU and so forth. And, oh, if you need to buy one, we can sell one to you. Yes. When you find out that half the African internet is still using something like a Cisco 2501 to do most of the backbones and so forth, and they multi-home quite happily, and they don't need 200,000 prefixes to do so. Anyway, backup link, we announce the 19 outbound. We use an MED because we're connecting to the same AS, so we can use metric. Lowest metric wins, so if we follow the defaults, the default metric is 0. So if you don't send a metric with your outbound announcement, the neighboring router will assume that it is 0. So if you send a 19 with an increased metric, then it becomes the backup path. So your AS100 will see a metric of 0 on the primary path and a metric of, I don't know, 50, say, on the backup path. Inbound, you receive the default route from your upstream on the primary link. The backup link, you also receive the default route, but what you do here is you tag it with a lower local preference. So default local preference in iOS is 100, so you just tag it with something lower, say 90, and that becomes the backup. When one link fails, because you announce the 90, or because you hear the 19 on the other link, you get backup. Because you hear the default in both links, you get backup. Okay, and this works very, very nicely. Looking at the configurations, well, they're actually very simple. These aren't configurations that I made up. These are configurations that I actually, well, retained when I changed jobs. So all I've done is change the IP addresses to protect the innocent. But the real live configurations that we used for our templates at UUNet. So you've got address block there, your /19. We send an aggregate out. This lets the aggregate out. We accept the default route in, and wow, that's all you need to do. So that's the eBGP configuration. That's all it is. It's as simple as that. Set up your neighbor relationship, put a nice description in there so you know where it's going. Filter prefixes in, filter prefixes out. You get one prefix in, you send one prefix out. Wow, that is very taxing. I mean, what sort of router do you need to run that on? Maybe one with about, I don't know, 1 meg of memory. Router B, slightly more complex, but you've got the /19 network statement here. You're still sending the aggregate out. You're still accepting the default in, but now we're applying some policy. Remember I was saying we're going to apply some policy for the backup link. So outbound, we've got router D out route map. Inbound, we've got router D in route map. And they are, router D out says if the prefix going out is the aggregate, we set the metric to 10. Default metric is 0, so metric 10 is higher. This makes it the backup. Router D in, well, anything that comes in, we set local preference 90. Inbound prefix that we hear is just the default route. So we set local preference 90, and that's us done. Okay? And it is as simple as this. And all that's missing from this configuration is an iBGP to connect routers, wherever it is, A and B together. And this works. This works perfectly well. If we look at router C, this is the upstream. Upstream providers don't tend to like doing custom configurations for each customer. They come up with maybe 2 or 3 options, and that's what you can have. So this configuration is very upstream ISP friendly, because they just do default originate to send a default route to their customer. Prefix list customer in, so they accept the customer address block in. Prefix list default out, they send the default route out. That's all they do. And they can replicate this configuration across all the routers that are aggregating customers onto the network. Don't blink. The difference between router C and router D for the backup, only thing that changed was the IP address there. That's all. Okay? That's what I said, it's upstream ISP friendly. They don't particularly care which is the primary path or which is the backup path, because their customer is sending the MEDs towards them. Okay? So this makes it very good. And the thing is, you can give your customer the tool. I mean, if it's not primary backup, but if it's something like load balancing, tell your customers, hey, if you want to change the load balancing, send an MED to do this or a community to do that. And, well, certainly my experience, the customers think this is a wonderful thing because they suddenly can get to play with BGP and so on. Router E, this is just connecting AS100 to the rest of the net. So we've stripped out the private AS there, so removed private AS. And then we've got a prefix list, which includes sending the customer /19 out to the internet. Okay? And that's that one. Now, as I was saying, that's probably not a very useful example. What people tend to want to do is load sharing. You buy 2 circuits, your upstream ISP, you tend to want to use both of them. Why buy a circuit just to leave it sitting idle? And you know what usually happens. You don't check that your idle circuit's actually working, so when you need it, you suddenly discover that it is down as well. That's not so good. So it's actually more common to use both circuits. So how do we do this? So this example, I'm just going to assume equal circuit capacity. So the link between A and C and B and D is the same capacity. It could be a T1 or T3 or OC192 or whatever. It doesn't matter. The principle is the same. Okay, so A and C and B and D, we're going to try and balance between these two. So what do we do? Well, the first bullet should be no surprise. We're going to announce our aggregate to our upstream on both links. We'll always do that. That's really, really important to do. And then what else? Well, in addition, we split the 19 and split it into 2/20s. So we're going to announce 2/20s as well. So we announce 1/20 on one link and the other /20 on the other link. Now, as you know, the most specific prefix wins. So a specific prefix will win over its parent aggregate. So if you announce a /20 out of a /19, traffic will always head for that /20 rather than anything announcing that 19. So what happens here is one path gets 1/20, the other path gets the other /20. So all traffic for the first 20 comes in one link, all the traffic for the other 20 comes in another link. Hey, you've got rudimentary load balancing. It's very, very rudimentary, but it's a good start. And that's where you start from. Take your aggregate and chop it into 2 pieces. See how you go. I mean, if that doesn't work so well, then maybe take 120 and split it into 221s. Maybe you need to split a 21 into 222s, and so forth. You vary that split until you get perfect load sharing. You don't do what so many people seem to do today is like, 19? Oh yeah, that's 32 Class Cs. If you see the amount of emails I get that say, hey, Philip, can you help me? I'm trying to load share with 32 Class Cs. And it's like, wow, you're not going to get those working on the internet today. But I think that, I don't say that to them, but that's the sort of thing that comes back. So we start again. We say, right, you've got your 19, split into 2/20s, see what you get. Vary the split until you get perfect load sharing. For outbound traffic, we just take the default route from the upstream. Okay? It's basic outbound load sharing by nearest exit. It usually works fine in the first approximation because your outbound traffic is minimal compared with your inbound traffic. For your customers are browsing the web, then who cares which outbound path the queries take? So looking at router A configuration, well, we've introduced the /19 there. We've got the /20 as well, the first /20. Outbound to router C, we're going to send the 19 and the 20. Inbound, we accept the default. And that's all there is to it. I haven't shown router B configuration because it's exactly the same, but for the second /20. Okay, so you just have 121.10.16.0. Okay, and that works just fine too. Router C, again, the upstream ISP, this is a nice friendly configuration for them because they don't care what's going on. They just know that their customer is announcing this address block and they may subdivide it. In fact, some ISPs now, and I see a lot of some of the transit providers do this, they just say, oh, well, we'll accept anything from the customer down to a /24. So the customer's got, say, a /19, you just do /19 up to /24. So the customer can do any subdivision of his address space he wants without having to phone the support people of his upstream. Upstreams like this. They don't want to be bothered. Okay? They don't like customers phoning them, asking them to do things. And that makes it actually nice and friendly for them. Router D configuration is exactly the same. The only thing that changes is the IP address there. Okay? So it becomes upstream service provider friendly. I mean, of course, if your customer is clueless and doesn't want to touch BGP, you can offer him a managed router service and put all the configuration there. Or you can put the configuration on your router here and manage it all at this end. It's up to you. I mean, some people will do that as well. But if you don't want to get involved in customer connectivity politics, then you just show them what to do. This is what you tweak and change and leave them to it. Okay, so load sharing configuration is only in the customer router. Upstream ISP simply has to remove the customer sub-prefixes from external announcements. And, of course, remove the private ASs. Rightio, where are we? A few minutes left. RFC 2270. Well, I mentioned this almost at the start. It's what to do when you've got multiple dual-homed customers. As I said, ISPs tend not to want to do custom configurations for each customer they connect. They want to try and standardize. And this is actually quite an interesting and useful technique to do. If your customer is really, really desperate to multi-home and he wants to multi-home between you and somebody else, well, you can break one of my rules early on saying get supplier diversity by saying, but we can connect you to different points of presence because at least retaining the customer on your network means that you don't stand the chance of losing him to your competitor. So it is a fairly valuable service. I mean, Internet MCI did this, and that's the origin of the RFC. And I mean, we did it as well. I mean, we had, I don't remember, probably about 15, 20 people who actually took this particular service back then. And it was very, very easy to configure, very easy to handle, and it meant that we had a way of retaining customers within our own backbone. So, what you want to try and do here is look at scaling the configuration. So obviously you're going to use all the shortcuts that your router vendor gives you. So for example, in Cisco cases, the peer templates, peer groups, and so on. So that basically every customer ends up with the same configuration. Let's look at a picture. Right, you're here, AS100, you've got all these customers all connecting to you, they're multi-homing onto your backbone at different points of presence. Yep, this slide is correct. There are no mistakes in it. Yes, each customer's got the same AS number. There's nothing wrong with that because you're giving each customer a default route. Default route says, I know how to get to the whole internet. So even though these people here are using different address space from these people here, they can still get connectivity around that way because they use a default route to get out, and then they see the specific prefixes to get into this customer there. So it works. You can use the same AS number. So that makes it nice and easy. So that's why I say earlier you see some ISPs will use single private AS number for the multi-homing customers or a public AS number, just depending on what they have. But this means it scales very, very nicely because you can give these customers all the same configuration. The only thing that's different is the address block that they have and the point-to-point link addresses. Okay, scalable service. You can teach your installation team how to do this. Very, very simple. It's another template. Templates are good. Okay, so custom announcements are the same as in the previous example. We use the same private AS. Address space doesn't overlap, so it's not a problem. Customer A1 configuration. Got the /19 and the /20 because we're going to do the simple load balancing. We let the 19 and the 20 out here. Inbound, we accept just the default. Router B1 configuration is similar, but for the other /20. Okay, we've seen this configuration before. It was the previous example. It gets interesting at the upstream, because the upstream gets in a configuration economy of scale. You can now set up a peer group. Or if you use your own other vendors, they'll have similar concepts as well. In the peer group, you can define the private AS. You can put the default originate. You can have the outbound prefix list. And then you just apply the peer group to customer 1, customer 2, customer 3, customer 4, 5, 6, and so forth. Inbound, you still have a different prefix filter. So a prefix filter will let just the customer's address block in for customer 1, for customer 2, for customer 3, 4, 5, 6, and so forth. It becomes a very simple configuration to manage. And then you just specify the customer prefix list there, and you're done. Router deconfiguration is virtually identical. It's just the point-to-point link addresses are different. And this is actually very easy to manage. Having run something like this myself a few years ago, it was very, very simple to do. It was easy to train the installation team to drop this configuration onto the aggregation router, and we didn't need to be involved. What about router E, where you connect to the rest of the internet? Well, you need to strip out the private AS. Okay, you strip out the private AS here, and then you have a prefix list, customers out. So you let the customer's address space out. If the customers have their own address space, you can just leak it out like that quite nicely. If the customer address space comes from your own address block, then aggregate it. Okay? Aggregate it. Announce the ISP aggregate. So the address block in the previous example all fit into this /13 quite nicely. Okay, so announce the /13 aggregate out rather than announcing the individual pieces. Always try and aggregate as much of your customer address space as you can. Because the internet's 200,000 prefixes, and I'm pretty sure that tomorrow we're going to hit the magic 2,000, at least in my BGP view. Jeff Houston's view is about 2,000 or 3,000 prefixes behind mine. So he's probably going to be about another 2 weeks or so before he hits the 200K. Okay, I think what we'll do now, let me just start this, because I've started a little bit late, otherwise I'm not going to be able to finish in time for the community meeting. So let me just move a few minutes into this, and then we'll have a break. So we're now going to look at multi-homing to different ISPs. In this case, we use a public AS number. Now you get some cases where people will use private ASs if it's agreed with the other ISP. I mean, we went down this path with British Telecom, BT's internet service in the UK. I mean, it was fine. We knew the engineer who was running BT's network, so it was no issue. But I mean, our salespeople really didn't get on at all with the BT salespeople. So they didn't smile too nicely on it when they found out. But from an engineering point of view, it was quite simple to do. But interestingly enough, we got a lot of emails from people saying, do you know that BT has stolen your address space? And we're like, what do you mean stolen our address space? Well, they've got this address block, and it's your address block. We looked up in the RIPE database, and it's assigned to you. Yeah, it's a block. It's actually been assigned to one of our customers. Well, how come BT is announcing it? Well, because they're multi-homing between. How does that work? And so we explain it. It's like, oh, that's illegal. I'll cover that in the next slide. It's called inconsistent AS. It looks as though two ASs are announcing exactly the same address block, and it's usually not a problem. The address space comes from both upstreams. I find that really hard to handle. I really wouldn't recommend this at all because it's too difficult. The days of ISPs being big, happy family have gone. Okay? It's now a very big competitive commercial business. So one ISP announcing somebody else's address space really does not go down too well. In fact, most people who sign up for services have to sign some clause in the service agreement saying, I promise upon whatever to never ever announce the address space I've received from upstream X to anybody else. So get your address space from the Regional Internet Registry. I'm sure Aaron have got a multi-homing policy like APNIC have, so you can go straight to them and get that. So the inconsistent AS that I just want to cover. What happens is you've got a private AS multi-homing between two public ASs. What it looks like for the rest of the internet is AS210 is originating this address block and AS200 is originating this address block. It's a nice command in iOS. If you just do show IP BGP inconsistent AS, you see all the prefixes that are originated from two different autonomous systems. And most of these, as far as I can ascertain, are valid announcements. Okay, so there's no real issue with it. But you get the usual thing of people jumping up and down, especially relative newcomers who seem to think that you can't have address space originated from two different ASs. It's not quite the same as having address space, the same IP address used on two machines on the same LAN. There's still people who jump up and down about any cast addressing, which I still can't comprehend either. But anyway, it's not bad, it's not illegal, there's nothing in the BGP RFC that says that you cannot do this. Okay, there's nothing wrong with it. But generally, when you're multi-homing between different autonomous systems, get a public AS number. It just makes it easier. Because if you try and use a private one, these two ISPs have got to agree which private one to use. And the problems can start there. So if we look at primary link, backup link, just quickly go through this example, again, for the sake of time. So the primary path is A to C, the backup path is B to D. What we're going to do is we announce the /19 address block on the primary path, so this is going to be the primary here. We announce the 19 out this way. To make this a backup, well, we can't use MED anymore. Remember when we were multi-homing to the same AS, we used MED. We increased the MED for the backup link. Well, you can try and do that here, and AS120 sees an increased MED, and he says, oh, that's nice, because there's nothing he can compare it with. MEDs are only compared if they come from the same AS, neighboring AS. So you can't use MED. You've got to use something called an AS path prepend. You make the announcement out here with a longer AS path. And the question is, how long? Well, before we come to that, we announce the 19 aggregate on each link. Surprise, surprise. Primary link makes a standard announcement. Backup link prepends the AS path by using the AS path prepend concept. When one link fails because you announced the aggregate, blah, 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 blah. Okay? Always announce the aggregate. That's really important. Looking at the configuration, well, router A is on the primary path. So we send the aggregate out. We accept the default in. BGP is really complicated, isn't it? I mean, we've got those few lines, and this is a working configuration. It'll work just fine. Router B, as before in the multi-homing to same provider case, aggregate out, default route in, but now we've got a route map to apply policy outbound and policy inbound. Outbound policy, we do an AS path prepend 3 times, I've decided. So it makes the AS path look 4 ASs long, rather than 1 AS long as it would have been before. How long do you make your prepend? Well, you don't make it 25 because, hey, that seems a nice number, as some people seem to do. Have a look at your neighbors. See how close your neighbors are to, say, some of the so-called tier 1 ISPs. I mean, go to, I don't know, Sprint's Looking Glass or AT&T or Level 3 or any of these guys. Go to one of the Looking Glasses. See how many AS hops it is to your 2 upstreams. And that way you can figure out what your prepend needs to be to get the primary backup effect working. Inbound, you just hear the default route and you set local preference 80 and that makes it the backup. Simple. Okay, as before, it's not a common situation to have primary and backup. What we want to do is load balancing. So the load balancing example is here. We announced the /19 out of both links as before. To get load balancing, we subdivide the address space. We send one /20 out one path, another /20 out the other path. Okay, so we send the first 20 out this way, the second 20 out that way. What happens? You sit out here on the internet, traffic for the first /20 will come in like this, traffic for the second /20 will come in like that. And you've got rudimentary load balancing. If this link breaks, then because you're announcing the 19 out this way as well, you get a backup going round like that. Okay? That's basic inbound load balancing. Okay, so when one link fails, you get all the backup that you want. You've got fairly basic load balancing. Obviously, in the real world, splitting into 2/20s is not going to work. But you start with this. You know, when you're searching through a list, the easiest way to search through a list is to do a binary search. That's what we're doing here. We're just doing a nice, simple, binary search. Okay, start with a /20. See how you go. Doesn't work? Well, try 21. See how that works. And so on. What was this? I've forgotten what this was about. Hang about. Yeah, sorry. Okay, so the configuration for this, we're going to send the 19 and the first /20 outbound. So first block is defined here. Outbound, we send something like that. We accept the default route in, becomes easy. Router B, we just have the second address block. So you notice the second address block is there. We send that out. Again, we accept just the default inbound. So we do nearest exit for outbound traffic. So it's very, very basic load balancing in this case, but it's starting with a simple concept and building upon that. Last example I want to look at before the break. I'm sorry for overrunning. Should have checked the lights before I started. This is another way of doing it. Okay, rather than taking the 19 and chopping it into two pieces, we can take the 19, announce it out of one link, we announce the 19 out of this link, and then just announce a single /20 out of that link. See what happens here. All the traffic for this /20 will come in this way, and everything else will come either this way or that way. So this is a bit more of a variable control. Okay, you've got the 20 here, you know all the traffic for this 20 is going to come in this way. If too much traffic comes in this link, make it a 21, see what happens. Or make it a 22, see what happens. So you get a kind of variable control just by modifying a single announcement. And this is actually what most people use to try and balance between two links like that. They announce the aggregates on both links, and then on one link, they announce a sub-prefix of that aggregate. And the sub-prefix simply depends on the bandwidth of the circuit and how much traffic that sub-prefix is attracting. And I've found that over the years, all the multi-homing situations I've helped ISPs with, this is what we end up doing. So this is the most common way of trying to do inbound load balancing. Okay? And the thing is, even if any ISPs out on the internet are doing net police style filtering, because you're announcing an address block that is within the registry minimum allocation size, even the announcement of this /20, it may only go 5 AS hops away, but you still get balancing between your two upstreams like this. I just wish there was something that indicated that I only want this /20 to be heard 4 or 5 AS hops away. Oh yes, there is. Work in progress. Some of you may be watching IDR and Joe Abley's appeal for support for the AS path limit attribute. If you hear about that, please, please, please support it, because it really, really assists this type of load balancing that people need to do. You need to go and basically support Joe so that the IDR pushes the draft forward, becomes an RFC, and then go and beat on your vendors to actually implement it. Okay? Because at the moment, people are just sitting saying, oh, we don't need this, we don't know what it does. Well, it makes this subdivision of address space not pollute the internet, and that's a really, really important thing now. End of rant. Okay, so we announce the /19 aggregate on each link. First link, we announce the 19 as normal. Second link, we leak a /20, and then with the /19, we can announce it with a longer AS path, possibly, or you can announce it as is. And the size of prepend that you use also gives you a kind of control too. You could do a single prepend, 2 prepend, 3 prepend. It very much depends. You've got 2 things that you can adjust. So it actually gives you a pretty neat way of controlling how much traffic comes in this link. Looking at the configuration, well, router A is nothing fancy. It's just aggregate out, default in. Router B, default in. Well, outbound we send, where is it, the aggregate and, well, the sub-prefix. I've done it a little bit shorthand here just to save space. The route map, router D out says, well, if we send the aggregate out, we're going to do a 2 times prepend, and we'll leave everything else alone. So that's a sort of example we could use here. And yeah, that's pretty much it. And this is frequently used for many, many ISPs that, well, certainly I've worked with around the world, and it works very, very well. Teach them the basic building blocks of how to do this. They quite happily go away chopping bits out of their address space to get fine-tuning for inbound traffic flow into the network. So as I said, this is commonplace. It shows how to do frugal load balancing without really doing too much pollution of the internet. The previous examples basically only dealt with load balancing of inbound traffic. So it's the announcements that we made outbound. And I've just said, well, just use default route for outbound traffic, which is probably fine for the internet edge where most of your customers are sitting there browsing the web. But it's not much good if you've actually got significant amounts of outgoing traffic. Also, if you're a transit provider, you're trying to balance traffic flows in both directions. You're trying to have more or less symmetric traffic flows. I mean, it probably doesn't matter so much in this part of the world, but certainly when you have a fairly geographically spread network, trying to keep that traffic flow symmetric is pretty important. For example, if you sit in parts of Asia, well, India's, or the Indian subcontinent would be a good example. Some ISPs get connectivity to Singapore or Japan. Other ISPs get connectivity to Europe. You don't want packets going out through Europe to get to the US and then coming back in through Japan or Singapore to get to India. Packets going around the world end up rather slow or taking a long time. So you want to try and have a look at traffic flows to keep them reasonably symmetric as well. So this is the original traffic engineering. We called this traffic engineering long before the MPLS folks came and adopted the terminology. And of course, balancing outbound traffic, well, if you ask what you have got to do for that, people just say, well, you know, you need the full internet routing table, don't you? And, well, as I was saying before the break, you know, you get your friendly ISP comes along and says, yes, that'll be a Juniper M7i, or it'll be a Cisco 7200, and you need 1 gig of RAM, and, well, that'll do perfectly, and we can supply you one if you want. It's actually really necessary to do anything like this. As somebody told me, you don't need the routing mallet to try and solve load sharing problems. Keep it simple, and it's often easier and usually a fortune cheaper than trying to carry n copies of the routing table. So some of the myths first before we go into this. First myth is that you need the full routing table to multi-home. Well, people who sell router memory would like you to believe this. Cisco sells some very high quality, very valuable memory. So if you want to buy lots of that and enhance our share price, go for it. It's only really true if you're a transit provider that you actually need to carry this full table. The full table can actually be a fairly significant hindrance to multi-homing. I mean, some of the bigger routers, you've got a fib that's got 200,000 entries plus all the internal entries. That can be a fairly serious proposition. The second one is, you need a big router to multi-home. If it doesn't fit into half a rack, there's no way it can run BGP. Well, actually, the router size is related to data rates, not running BGP. I mean, I've run BGP on little things like Cisco 800s. I've run BGP on you've seen the Sycrus boxes, which are no much bigger than a mobile phone. They run BGP just fine. In reality, you need 2 interfaces. You need to be able to talk BGP to 2 peers, handle BGP attributes, and handle at least 1 prefix. So that's not exactly a big ask. And the third myth is BGP is complex. I mean, people who do BGP consulting services and so forth always try and, well, remember Mongolian example. BGP is complicated. Well, you know, if you touch the router, you might break it. I remember my boss's first instructions not long after I'd started at that ISP in the UK. I'll give you the enable password to the router as long as you promise not to touch the BGP bit, because if you touch the BGP bit, you'll break the entire internet. Yes, well, in the wrong hands, BGP certainly can be complex. If you keep it nice and simple, it's all actually pretty easy. So looking at some of the strategies. Well, first thing to do is look at the net flow data for popular sites. If you've got Cisco boxes, you'll be very aware of net flow. I believe most other vendors have got a similar sort of thing that will actually give you sources, destinations, TCP, UDP, ports, and all the rest. Have a look at that data. See where your customers are going, what sites they're browsing, the popular destinations. Is it really all going to Yahoo or Google or Hotmail? figure that out, because you may want to optimize your external links and your peering relationships to suit those paths. Secondly, prefixes originated by your immediate neighbors, and their neighbors will do more to aid load balancing than prefixes from many AS hops away. When we're sitting in the US here, who cares about prefixes coming from, well, Central Asia or Central Africa? It's not going to help your load balancing, so wasting time trying to fine-tune those doesn't make any sense. They're going to be 4, 5, 6, 7, 8 AS hops away. So concentrate on local destinations, because they'll be more static or more stable than destinations further away. The internet changes. Every minute the internet looks different. So there's little point trying to fine-tune load balancing for things that are going to change as soon as you're finished. Thirdly, use default routing as much as possible. Okay? The default routing, if somebody gives you a default route, they're basically saying, I know how to get to the full internet. I know how to get to the rest of the internet. Okay? If you want to use a full table, use it carefully. Remember, it's a very, very heavy load for your routers. I'm going to cover 4 examples. Hopefully I've got enough time to do them. Got 1 upstream, 1 local peer. Going to look at upstream and a local exchange point, 2 upstreams and a local peer, and then 3 upstreams with unequal link bandwidths. All these need BGP and a public AS number. We're going to assume that we've got a /19 address block for the network in question. So the first one, 1 upstream, 1 local peer. This is a pretty common situation in many parts of the internet. You connect to your upstream transit provider to see the internet, and you connect to the local competition so that local traffic stays local. Okay, so that's fairly normal. This is your situation. You've got 1 router connecting to your local peer. You've got another router connecting to your upstream. You keep them separate. Notice I've got 2 different routers here. If you put it all in 1 router, well, if that 1 router falls over, you've lost all your connectivity. At least in this example, if router C fell over, you still can talk to your local peer. In some places, you may even have backup arrangements with your local peer. What we're going to do, we announce a /19 aggregate on each link. The first bullet is always the same, each example. Accept just the default route from the upstream. You've only got 1 upstream, only 1 path. So you only need the default route. You don't need the full table. So usually your upstream will give you the default. If the upstream doesn't want to give you the default because he's afraid that you're going to leak it to the internet, then take a network, which you can use as a default, or just talk BGP with them, but use a static route for the default. And you accept all prefixes that the local peer originates. Okay, so all traffic will go to the local peer. So for local traffic, and everything else will go through your upstream. Configuration, where did I put the pointer? Here. Configuration, you've got your network statement for the /19. You send your address block out, and inbound you accept all the prefixes that your local peer is going to send. So for example, they could be sending these 2 prefixes, and that's what you do. It is straightforward as that. And connecting, well, sorry, the other configuration that you can do is using a filter list. So you filter based on AS path. Now the reason for that is, well, prefix list is fairly high maintenance. So if your local peer gets another address block, you've got to go and update your filter. So he's got to send you an email saying, please update your filter, accept my new address block. And that could be a bit of a nuisance. So if you trust your local peer a lot, then you can just use a filter list, an AS path filter. So anything that he originates, you accept. I would only do that if you know the other provider really well, because anybody can make mistakes. And they could accidentally start announcing you all sorts of garbage, and you'd have no protection against it. In fact, what you find these days is that some people actually use both a prefix list and an AS path filter list. Onto router C, going to the upstream, we just accept the default route, and outbound we send just our address block. So this is a very, very simple configuration. This works. I've put this on many, many ISPs around the world. The only thing that is missing is the iBGP configuration between router A and router C. Okay. As I was saying, 2 configurations are possible for router A. Filter list assumes the peer knows what they're doing. I mean, if the engineer at the peer is your best friend and you know him really well, or you grew up together at school or something, then fine, you can trust them. If it's somebody you've never really heard of, try and be a bit more cautious, use something like the prefix list. It is higher maintenance, but it is a lot safer. And as I said, some ISPs use both. If you accidentally blow away your prefix list, at least your AS path filter is there as a backup. For what it is worth, we actually always used double configuration. Prefix list was always backed up by our AS path filter. And that's it. If you got, this is just a configuration aside. If it's a private peer and you don't want to provide them transit to the internet, it's really important to make sure that the router that is connecting the private peer has no way of allowing packets from them to go all the way out to the internet. So it's really important not to have a default route on this router or put filters that block packets destined for the internet. I tend to find it easier, rather than do packet filtering, it's easier just not putting the full routing table onto that router A. So all you do is, in the iBGP with router A, you only allow local prefixes. And that way your local peer can only access your network and not get accidental transit. I've seen many situations where people haven't been careful and their local peer has actually used them for outbound transit. Okay, they just point a static default route to you, and all their packets go out through your network out onto the internet. And if you don't have much outbound traffic and they don't have much outbound traffic, you'll never notice. It's only when something goes really wrong, like they host spammers or something, that maybe you find out that they've been stealing your bandwidth. Second example is one upstream, the local exchange point. This is very similar to the local peer. It's just we're scaling the local peer part. So it's like this instead. Your router A is now at an internet exchange point, so it plugs into an Ethernet switch where other ISPs are as well. What do we do here? We announce the 19 aggregate to each neighboring autonomous system. We accept just the default route from the upstream. We don't need the full table. There's no need for it. All the exchange point participants send us the prefixes they originate. So we get all the local prefixes, and then we send everything else to the upstream. Again, a very simple configuration. And it's one of the things I do in my spare time is, well, part of my day job is help set up internet exchange points in many different countries and regions of the world. And the technical part of setting up an exchange point is probably 10% of the difficulty, but people seem to get completely stuck when it's doing the configuration part. And when we end up showing them how simple the configuration actually is, people go, yeah, but there must be more to it than this. And there's never more to it than this. And it's actually surprisingly straightforward. Because it's an exchange point, you've got many peers that all have you have the same policy with, you can use shorthand. Like you can use a peer group here, so you set up an exchange point peers peer group. You've got, put your address block in there because your address block announcement is going to be the same to all of the peers, the participants at the exchange. Strip out any private ASs, that's like best current practice. You've got a route map here to set local preference high, so that even if you hear the exchange point peer prefixes through your upstream, for whatever reason, you're still going to prefer them through the exchange point instead. And it makes this RPF check actually work without accident as well. If you don't know what the RPF check is, well, ask me later, if you wouldn't mind. And then you can use the peer group and you just apply to all the peers. So AS100, 101, 102, 103, same configuration can be used for each one. The only differences are the inbound filters for each peer. That's all you need to do. You just otherwise use the same configuration. And then we've got the prefix list for each peer, peer 100, 101, 102, 103, and so on and so forth. Here we forcibly set the local preference high, so higher than the default of 100. And that way we always prefer outbound path through the exchange point for these particular peers. Okay? So that's generally how we handle connecting to a local exchange point. Note that router A doesn't generate the aggregate. If you're watching really closely, you'd have spotted that there was no network statement on that configuration. There's a reason for this. If your router is sitting at the exchange point, it's obviously not going to be in your local data center. It's going to be somewhere else. What happens if the link between the data center and the exchange point breaks? Well, if you were originating your aggregate at the exchange point and the link broke, well, you'd still originate the aggregate at the exchange point. You may get backup through your upstream, so outbound traffic goes through your upstream. It will reach your exchange point peers through their upstream. Where would the response traffic go? Well, they would see the best path through the exchange point. So the response packets will go across the exchange to your router, and your router would say, oh, I'm announcing this prefix, but the only place I can send it to is the null interface. And so the packets get dropped. So doing this, you basically cut yourself off the network. So a really important thing is when you originate an aggregate, originate it within your network, not somewhere remote. Okay? And I mentioned the route map already. For the upstream configuration, pointing to the upstream, it's the same as before. Default route in, your address block outbound. Okay, straightforward. Yep, okay. Just for the exchange point configuration recommendation, same advice as it was for the local peer. Be aware that the exchange point border router should only carry the prefixes you want the exchange point peers to receive and the destinations you want them to be able to reach. Yes, you can put packet filters on to protect against this if you like doing packet filters, but I much prefer to use the routing reachability to handle this, as it's less CPU intensive or router intensive on trying to use packet filters. If you carry the full internet routing table at the exchange point, it means that exchange point peers, or even people you don't peer with, can point a default route at you and use you for outbound traffic. Imagine a content provider, legitimate or not, they could just point a default route at you and serve all their content out through your network. Why am I making such a big deal about this? Well, I see it happen quite a lot. Even we got burnt twice, way back in the early days of the links in the UK, where one of our customers who was at the links but we didn't peer with pointed a default route at us and used us for all the outbound traffic. And we didn't actually notice until we finally got a NetFlow image from Cisco and saw all this outbound traffic though, from a source that we didn't even know about. And finally, the second point, if the IXP router is at an exchange and distant from your backbone, don't originate your address block there. I mean, again, I've got an example of that, but it's similar to what I just said could be a problem. Right, next example, 2 upstreams, 1 local peer. So far we've said, well, you know, default route from your upstream is just fine. What about when you've got 2 upstreams, 1 local peer? Well, the local peer, we've done that. That's simple. But 2 upstreams will give you external redundancy and diversity, and it's often the reason that any provider will multi-home. It's like this. Notice I've now got 3 routers. You can merge routers C and D, but then you don't get router redundancy. If you merge C and A, well, then your local peer can potentially send traffic out through your upstream unless you put packet filters in place. And that could be a bit of a heavy load to do, especially if you've got a large number of local prefixes. So I deliberately separated these 3 routers out like that. What do we do in this case? Well, we announce the /19 aggregate on each link. Okay? We always announce our aggregate block. We accept the default route only from the upstreams. Okay, this is getting back to the example we had just with a simple multi-homing before the break. Accept all routes from the local peer. Note the separation of router C and router D. Router A is all the same as before, as I mentioned. So let's look at router C. Simple configuration, we accept the default inbound, accept the default in, we send our address block out only. Okay, so our address block, we generate it here, and that's what we send out. We look at router D. We do exactly the same thing. The only thing that's changed are the point-to-point link addresses. This is fine, but quite frankly, it is not a lot of use. Okay, it's not a lot of use because you've got no outbound traffic engineering at all. Okay, you're just using nearest exit. The routers closest to C will go out through router C. The routers closest to D will go out through D. You've got no way of engineering or load balancing outbound traffic. We know how to do inbound traffic engineering. It's simply how we announce our prefixes. We've covered that. We've seen all the tools that are available. So that's done. But what about outbound? Well, the 2 options. The first one, the favorite, the world's favorite, is to accept full routing from both upstreams. But that's actually pretty expensive. And I always say it's actually quite unnecessary to do. How do lesser developed parts of the internet manage to do multi-homing today without having monster routers? Because what they do is they actually accept the default from one upstream and some routes from the other one. So rather than having 400,000 paths on a router, they probably only have 10,000 paths. And they have exactly the same load balancing effect as somebody who's got 400,000 paths. Quite extraordinary. And the thing is, if one of the links fails, BGP will fail over very, very quickly compared with the people who've got 400,000 paths, where the poor router hits 100% CPU, at least as the control engine tries to recompute the routing table. Okay, so let's have a look. If we did this with full routes, what would we have to do? So we have got the /19 here, we announced that. Outbound, inbound, I've got this route map called AS130 load share, so we'll look at that on the next slide. Prefix list, RFC 1918 deny in. And what the box says, allow all prefixes in apart from RFC 1918 and friends. Who are RFC 1918 and friends? Well, they are basically the famous bogon list. I think Rob Thomas has got the best definition of what those are. See www.gumri.com/documents/bogonlist.html. Remember I mentioned the bogon feed before? That's the alternative way of doing this. So you don't even have to do the filter. Okay, but if you want to use his prefix list, you can just pop it in there and just remember to keep it up to date all the time. Looking at the next slide, what's this AS130 load share route map? It's not some secret iOS configuration, but something you've got to define yourself. Match IPAS path 10. Okay, IPAS path 10 is this thing. Anything that matches this, we're going to set local preference 120, otherwise we set local preference to 80. Remember, we're getting a full BGP feed. Remember, I said earlier, what to do is concentrate on local prefixes. So what this AS path filter does is, any prefixes originated by 130, which is my I keep dropping this. Anything that's originated by AS130, anything originated by AS130 will match this, and we set high local preference. So this says, anything coming from 130, we want to go out through 130. It doesn't make any sense to have it going out through the other AS, whatever that was, 120 probably. It doesn't make any sense for it to go out around the other way. Okay? You want to take the shortest path. You want to try and have things as symmetric as possible, certainly for neighboring ASs. And this also says, well, take anything originated by AS130's neighboring ASs. So this funny thing here says any number between 0 and 9 repeated at least once, so that matches a number. So anything that's 130 with another AS behind it will also match. So anything originated by AS130's immediate neighbors. Okay? So if you see what that's doing, outbound traffic for AS130 and their neighbors will go out through AS130. Traffic for the rest of the internet, who cares? It might go out through 130, it might go through out the other way. Okay? So that's the goal here. So that way you try and get some symmetric traffic, at least to these neighbors. What about router D? Well, we'll get a full table here as well. Okay, so RFC 1918 denies, same old bogon list. Take everything, throw away private address space, non-routable address space, and so forth. So you end up with roughly 400,000 paths on this. Maybe 10,000 paths have high local preference, say 120 local preference. You've got 200,000 paths of 100, and then you have 100 and, what did I say, 10,000? So 190,000 paths with 80 as a local preference. So your poor old router's got 400,000 paths to try and churn through to get the best path. And that's what most people do today. Okay, so that's basically what I've just said. Issue here is it's expensive. You need a lot of memory to handle this. 2 full BGP feeds today, certainly in a Cisco box, is 256 meg of memory minimum. Okay, that's, well, it's fine if you've got the big routers and so forth, but for guys who are still using last century's equipment, it's a bit of an issue. And it needs lots of CPU. It's fine you've got the latest and greatest CPU on the latest routers, but if you're still struggling with Motorola 6830s, it's going to take, well, tens of minutes to try and churn through 200,000 prefixes. You need to play preference games. You're changing preference on about 200,000 prefixes, and that's not such a good idea either. It's only an example, but this is a fairly common example that I've actually seen. Doesn't consider inbound traffic, but we've done that sort of thing before. So the strategy, what you want to try and do is have a look at partial routes using this sort of strategy. We ask one upstream for a default route. The default route basically says, I know how to get to the whole internet. So the default route is being used to replace 200,000 prefixes. You ask the other upstream for a full routing table. Yes, that is not a mistake either. You ask them for the full table. But what you're going to do is you're going to throw most of this full table away. The upstream ISPs don't want to do custom configurations. They're happy to give you either a default route or a full table or maybe something in between, but they don't want to customize it to your needs. Okay, so you ask them for upstream for a full table. We're going to filter this based on the neighboring AS. For example, you want traffic to their neighbors to go over the link to that ASN. So most of what they send, you're going to throw away. So the router C configuration, probably something like this. So router C is the one we're going to ask for the full table. We're going to do the usual bogon filtering, so throw away the prefixes that shouldn't appear on the internet at all, so Rob Thomas's list. Outbound, you're going to send just your address block, and then you've got your inbound AS filter. So what this is going to do is accept only the prefixes from them and the neighbors. So filter list 10 is down here, accepting just their prefixes that they originate and the prefixes that their neighbor originates. And I should switch off my phone because it's ringing like mad. So accept the prefixes they originate and what the neighbor originates. So this is doing exactly the same as we had before in the full table example. With one exception, we're no longer having 200,000 prefixes on our router. We're taking just the prefixes we need to multi-home, so say 10,000 prefixes. Router D goes back to simplicity. We accept just the default route, and that's it. So in router C and router D on our network here, we just have 10,000 prefixes and a default route from router D. So router C, one thing we're missing a default route. We have not heard a default route from router C. They're just sending us the full table. We're throwing everything away. So how do we do the backup? Well, the way we do the backup is we then step into the IGP. And it's something like this. We point a static default route to the upstream. So on router C, static default route to the upstream, say the upstream link is on 000, or it could be on packet over sonnet link or whatever, it doesn't matter. And you make it a very, very long distance. So make it 254, which is the least important distance. Because static route is normally 1, remember? Make it 254. As long as the serial interface is up, this default route will be put into the routing table. If this default route is in the routing table, OSPF default originate command will work, so the OSPF will originate the default route into OSPF. So this way our backbone sees the default route. Likewise, on router D, we hear the default route by BGP. We want to do the same thing. We point a static default on, again, the WAN link going to their upstream. Again, with the distance 254. Here we make the metric 10. So this is going to be the primary path for backup. That's going to be the backup path. Again, if this static route works, the default route will be dropped into OSPF. So now OSPF has got a default route coming from both edge routers. So if the link, router D link goes down, this default route disappears, OSPF will stop originating the default, so this one will take over because it's a higher metric. So your backup default points to this, the static route points to the upstream, so all outbound traffic will go through the AS130 link. Okay, so that's the alternative way of doing it. You're dropping the default route into OSPF, and you get very, very quick failover. The amazing thing is, this fails over in the rate that OSPF fails over. And if you tweak the timers, this can fail over in 2 seconds if the external link goes down. Whereas the full BGP feed, well, I tried it on something like, what was it, 3725 with a full table, and it took about 10 minutes just to work through 400,000 paths. I prefer the 2-second failover myself. Okay? So this is actually much, much more efficient. You've only got 10,000 prefixes to deal with. And it actually works a lot better than trying to do the outbound load balancing with 2 copies of the full table. Okay, so partial routes from the upstream, use OSPF to determine the outbound path, D default as metric 10, C default as metric 30, that becomes the backup, D is the primary, 0 goes down, the static default is removed from the routing table, and the OSPF default is withdrawn. Okay, an amazing thing is this is not expensive. Would have got exactly the same effect. In fact, this is faster than using the full table. And the amazing thing is you probably only have 10,000 prefixes on the router, 10,000 paths, rather than 400,000. You're not playing with any local preferences whatsoever. No local preferences at all. Default route from one upstream, 10,000 prefixes from another upstream. Okay. By the way, when you're distributing internal default by IBGP or OSPF, watch your local peer router and watch your exchange point router. If you're putting the default into OSPF, of course, it's going to propagate it to your exchange point router or to your local peer router, which means it has a default. Again, I say you can use packet filters, but it's much easier just to use the routing system. Just have a static default route on these peering routers point to the null interface. Then if anybody tries to point a default to you, this packets are simply dropped into null. Okay, because that will override, because this is a distance of 1, this will override the default route propagated by IBGP or by OSPF. Okay, now, how much time? This one's a fun one. I've added this one, if anybody's sort of been comparing slides from now and previous NANOGs. This is a new example. Autonomous system has got 3 upstreams, and we've got different bandwidths. I mean, this is a real practical example, and actually this example is stolen from 2 months ago when I was at SANOG, and I was working this for one ISP at SANOG. And it was basically they had an 8 meg link to one provider, a 4 meg link to another one, and a 2 meg link to a third one. And they were like, how do I multi-home with this? And their solution was, well, I've got 32 class Cs from APNIC, and I'm just going to announce them all out on my different links, and we'll see what happens. And that's what they were doing. And in fact, they didn't have any redundancy either, because they weren't announcing all the class Cs out of each link, all the /24s. They were just announcing some of them, and it was all generally fairly shambolic. So what was the strategy here? Well, the option, certainly for outbound, is to get full table from each upstream provider, which is what they were doing. 600,000 paths they had on their router. I think it had 512 meg of memory, and it was using a lot of it. 600,000 paths. Another option is partial table and defaults. So I said to them, well, why not using partial table and default routes? And it was like, huh? Didn't know you could do that. How can you do that? How can it all work? Well, this is a diagram, because you've got 3 upstreams. I mean, you only need 2 external routers for your upstream. So we connected ISP-A, which is the 8 meg link, to one router, and the 4 and the 2 meg link to the other router. There's a slight method to my madness here, a slight madness to my method, because this is the biggest connection, and then we've got 6 meg coming in here and 8 meg coming in there. That was the logic I was following. Okay, so what do I do? Well, the BGP feeds available from transit providers these days tend to be these. You either get the full table, or you get customer prefixes and a default route. This one seems to be getting more and more common. I can't really quite work out why this is. They send the customer ASs and the default. And you get the default route. So they send just 000/0. These are the common options. I find it very, very rare these days for any provider to offer anything else. I mean, there's nothing wrong with it. I'm just saying this is what it seems to have fallen into now. So what's your strategy? Well, accept only a default route from the provider with the largest connectivity. So the provider who's giving you the 8 meg connection in this example, we accept just the default from them. So we send them an email saying, give us a default route. Because most of the traffic is going to use this link. Most of your inbound and outbound traffic will use this link. It's the biggest pipe. Okay, it's about 60% of your capacity. If ISP-A won't provide a default, well, you still talk BGP with them. Okay, you use BGP to send your address block to them. Get them to send a full table and throw everything away. Just have a default deny. And then you point a default route to them and distribute the default into IGP, as I showed you before. You request the full table from B and C. And it's like, it takes you a second or two to think a bit about this. It's like, hang about, You've got the biggest link and default route and the small ones, full table. Most people seem to think biggest connection, full table, and the smaller ones default route because the BGP updates take a long time to squeeze down a 2 meg link. But the logic here is this. You're going to throw most of the table away. So it doesn't matter how long it takes to first load up. You're discarding all of it. Okay? I don't find any use in the default route plus customers. I don't know why people are offering that. I have not found any situation where it's actually been useful. But somebody's obviously decided this is a good thing to do. If somebody would enlighten me, I would be really happy. How do you decide what to keep and what to throw away from ISPs B and C? Well, most traffic is going to use the ISPA link. So what you need to do is find a useful subset of prefixes to receive from B and C. So what my strategy has been over the years, and I found this actually works pretty well, is discard prefixes transiting the global transit ISPs. And of course, that opens that particular can of worms. Who are the global transit ISPs? Because everybody tries to claim they're a tier 1 or not a tier 1 or whatever. And, well, it's always a very controversial thing. So for B and C, I discard the global transit ISP ASNs. Any prefixes transiting those I throw away because those have crossed the internet core and we should be hearing those through the biggest link. Discard the prefixes with ISPA's AS in the path because you're going to hear those through ISPA. That's what you want to be able to do. I reckon the global transit ISPs include these. I I didn't make these up. This actually came from work that was done by Gaurav Upadhyay and Vijay, his colleague Vijay from Nepal, who are trying to actually look for anomalies within the AS path. It's actually a presentation I'd quite like to get here at NANOG, but it was actually really interesting because they're trying to look for interesting anomalies where little ISPs or internet cafes were providing transit between UUNet and AT&T and so on. That's what their main aim was. But they discovered that, well, these ISPs only ever appeared twice in an AS path. You never saw any of these appearing 3 times, or 3 of these appearing in any one AS path. So that was an interesting side effect of it. So it's quite interesting. Anyway, so I picked those, just for no other reason. So in my AS path filter for the B peering, I dropped any prefixes that had these ASs in the AS path. I dropped ISPA, I dropped ISPC's AS, and then allowed prefixes originated by ISPB, ISPB's neighbor, and their neighbors, and their neighbors. This you can make as big as you actually want. I mean, this is just an example. The way you would start is just pick this one and maybe the neighbor. If it's not enough, then add another one in. If it's not enough, add another one in, and so on until you get enough traffic going out to the ISPB link. And you deny everything else. You do the same thing for the ISPC link. Throw away all these guys, throw away ISPA, ISPB, and just permit C, neighbors, and so forth. Okay, and that lets you send traffic that is local to ISPB and ISPC through the ISPB and ISPC upstream connections. Okay, it seems to work pretty well. As I say, this is an example. This is not an exact recipe of what you must do. This is an example that has worked for me. So part 1, we're dropping the global transit ISP prefixes. It can be fine-tuned. Maybe you want to accept one of my list of tier 1 ISPs within. I've found sometimes I need to do that. If one of your transit providers is one of those 8 that I listed, then it's a bit silly to drop their prefixes. Okay? So you need to fine-tune it accordingly. More prefixes you allow in, the more traffic you get out, going out. Dropping prefixes transiting ISP A and C network, permit prefixes from ISPB and their neighbors, and so forth. And you massage the AS path filter until you get the amount of outbound traffic that you want. Do the same thing for ISPC, as I was saying. You may have situations, I mean, this was written with South Asia in mind because it's a South Asian example. ISPB might be in Japan, neighboring AS might be in Europe. Check those because some of the non-tier 1 ISPs still pop up in many parts of the world. I hope I don't offend them, but for example, BT Ignite and Reach. Both of these ISPs are in Japan and London and various other parts of the world, even though BT Ignite is more European network and Reach is more in Asia backbone. Yet they still appear in London and various other parts of the world. Okay, so you need to try and watch that sort of thing, that the AS path length may not be the most logical thing to look at. So have a look at the geography as well. Okay. Inbound load balancing strategy. Largest outbound link should announce just the aggregate. Just send the aggregate out, the biggest pipes. The 8 meg circuit, aggregate out, default in. Easy configuration. The other link should announce the aggregate with an AS path prepend. The size of the prepend depends on what the topology is. So it could be a one-time prepend, two-time prepend, whatever. Announce sub-prefixes of the aggregate chosen according to traffic volumes to those sub-prefixes. Have a look at your address planning. If you leave your address planning to some administration department, you're probably making a mistake. Address planning within the backbone, in my humble opinion, should be done by the network engineers running the backbone, because the addressing scheme that you use has a fairly severe impact on the load balancing. Okay? You don't want to put all your data centers on 1/24 because that might be 90% of your traffic. It makes it impossible to load balance there. But I run into this example all the time. You've got broadband customers and dial customers all using a single /24, and it's 90% of the ISP's traffic, and he says, yeah, I'm trying to load balance, but I've chopped into 24s and still 90% of the traffic coming here. Well, this is not going to work, because the majority of your traffic is in the 24. Oh, well, but what do I do? Well, how about renumbering some of your broadband customers? Use 2/24s at either end of the range. Oh, but I can't renumber dial-up customers. Why not? They're dynamically assigned. Oh, but, well, it might break something. Maintenance slot, shut down the server, change the address pool, bring it back up again. Nobody's going to notice. They're all BitTorrent people just sitting there sharing files. And seriously, that's what it is. They're all like that. Nobody really notices at 4 o'clock in the morning. So you can renumber it. And the beauty with doing something like that, you've got broadband at either end of your range. You can then take your address block and divide it into 2. And amazingly, they got load balancing. And you're like, gosh, this is just amazing. But it's not amazing. It's just applying a little bit of thought to how you do your addressing plan. Okay? Oh, here's another example. ISPC could be used just for commercial leased line customers. So if you number all your leased line customers, these are the guys who pay you lots and lots of money for high value service, announce the address block that they're using out through ISPC. So your broadband dial customers are never going to send all the BitTorrent junk in through this particular link. You can reserve that circuit just for your high value customers. It's how to use the addressing plan in your network just to do load balancing, and how to do the quality of service in your network. You don't need to then end up playing around with all these crazy commands that the vendors like inventing for the routers just to do quality of service. If you do your addressing plan sensibly, think about the services, think of external links, you can do it quite nicely like this. Okay, the router A eBGP configuration example. As I said, this is going to AS110. It's the big fat pipe, the 8 meg circuit. Simple, default in, aggregate out. This is taken off a router that I configured 2 months ago. Addresses changed, AS numbers changed. It's exactly that configuration they got. Nothing more, nothing less. Router B, again, this was just taken straight off the router. We had, where's this going? So this is going to 120. This is the 4 meg connection. Prefix list ISPB out, filter list 1 in. So they told them to send the full table, accept. This filter list 1 basically accepted, that's on the next slide, we'll see in a second. The route map does the prepend. Same for ISPC, this is a 2 meg connection. Okay, again, outbound we send our address block, the /19 or whatever it was, filter list 2 in, and then the route map as well. Let's look at the route maps. So the ISPB, hang about prefix list, so we send the 19, okay, 121. This 21 is for our dial customers. This 22 was for our business customers. Okay? That's the sort of thing we've done. We've chosen to send our business customers out towards ISPC, our dial customers out to ISPB, and the rest of the network, say the broadband people, the wireless people, they go out through ISPA, the volume. And if the ISPA link fills up, too bad. That's the quality of service the broadband customers get. And then the route maps, well, to ISPB, we're doing a single prepend on our aggregate. To ISPC, we're doing 2 prepends on our aggregate. And that gives us backup and some inbound traffic as well. Okay, and this one works pretty nicely. I'm going to say it was just stolen off work I did 2 months ago. So we have default route from ISPA by eBGP, mostly discarded full table from B and C. In this case, it was about, I'm trying to remember, I think it was about 15,000 prefixes we ended up on this network. So it's a bit of a reduction from 600,000 to 15,000. The amazing thing is, when one of these links failed, the network failed over to backup connections almost, well, it was within a few seconds. Whereas previously, they were taking many, many minutes to do the same failover. As for the default route, going out, well, strategy was to originate a default by OSPF on router A with metric 10. That was the 8 meg connection. Originate a default on router B with metric 30. On router B, we've got a static default with this distance, on C with that distance, so we've got different static default distances. When the link goes down, static route is withdrawn, OSPF stops originating a default route. The reason I have these two is I want the traffic to go for ISP B. So if A fails, I want it to go for B first, because B has the bigger link. That's why I've got different distances here. If B fails and A fails, then it will go to C only. That's the motivation. Okay. So the steady state, all links up and active. Router A is the default route because that's OSPF metric 10. Backup default is router B, OSPF metric 20, going throughout ISP B. Sake of time, I'll just whistle on quickly. If the link to ISP A goes down, B and C is still up. Default route is to router B. Upstream is router B. Above is also true if the B and C link is B or C is down as well. Link to ISPs B and C down, so both of them down. Link to ISP A is up. That's the default route. The static default disappears from router B, so OSPF on router B withdraws the default. Other considerations you need to think about. Thinking about considerations. Anyway, default route should not be propagated to devices which are terminating non-transit peers and customers, as I said before. So simple static default to null interface, just in case. Or if you're propagating it by BGP, put in a BGP filter that blocks the default going to those particular routers. In fact, I generally just say there's no need to carry a default around in your network per IBGP. You use OSPF for that. OSPF will fail over much, much quicker than than BGP ever will. Okay, unless you really, really crank the BGP timers. So use OSPF for the default route. The failover will be really fast. We still carry other eBGP prefixes across the IBGP mesh. Use that because then the aggregation routers will be able to do best path to the exit rather than following the default route. The default route may not take you to the best exit point. So you may end up going to one exit and that router saying, well, hang about, the best path's actually out through the other one. So this might help with traffic distribution across the backbone. So still carry the other eBGP prefixes you've learned. It's not such a big issue, but it just tidies up the traffic flow within your own backbone a little bit. The IBGP configuration, well, just as an example, we set up the IBGP peer group, IBGP filter out, which says block the default route, allow everything else. That's all that's doing. Or you can use a community filter. If you tag all the local prefixes with your local community, then you can just send out the prefixes by IBGP that belong to the local community. Either or, but prefix filter works as well. And then you just apply it to all the IBGP neighbors. So I've listed 2 there, but there could be N more. Okay, so this is actually based on many deployed working multi-homing load balancing topologies. As I said, this one is one I stole from work I did 2 months ago with a certain South Asian ISP. This is just an example. But if you use this example as a starting point, it's very, very easy to tune because you can add or subtract from the list of ASNs that you're filtering out of. It's got a huge advantage of being really, really light on border router resources. It's very light on the backbone router infrastructure. It gives you a very sparse BGP table. The convergence of this is much, much, much quicker than trying to handle 600,000 paths. Okay? Unless you've got the super duper amazingly fast process, the latest one, or using latest PC router or something, there's no way that you can handle this in a sensible time with 600,000 prefixes. Okay, final section. I did this really quickly. Sorry for that. If I went too fast, have a look at the recording later and play it at half speed or something. Using communities, just a few slides on those. This is about how they're used in practice. So I've just collected some communities as ISPs have used them in the wild. Firstly, have a look at RFC 1998. Again, this is work by a couple of guys, Internet MCI, way back, in probably about 96, late 95, early 96. I think it was Tony Bates and Enka Chen who documented this. It's what they did when they had Internet MCI, but how they use communities to assist with their customers' load balancing onto their network. So it describes how to implement load sharing and backup in multiple inter-AS links. And the idea was to actually simplify the upstream configuration and give the customers some control. And the communities defined in this RFC, which is just an informational RFC, was, well, if the customer sent, say, local AS and community :100 as a community, you would set local preference 100 on that particular prefix. If they sent this ISP AS :70 as a community, then you would set local preference to 70, and so on. How does this translate into real life? Well, a customer router configuration could be something like this. Remote AS 100, this is our backup ISP. We're going to send, rather than sending any MEDs or AS path prepends, we're actually going to have a route map which is going to set communities on the outbound announcements. So the communities listed here, anything that matches AS path 20, so anything originated by the local AS, we set community 100:90. So that community goes with the prefix announcement to the upstream. The upstream says, oh, he's sending me his prefixes with community 100:90. That means I've got to set local pref to 90. And so the prefix announcement, he sets local pref 90 rather than trying to rely on MEDs or AS path prepends. So this is actually a tidier way of trying to do things. And on the upstream ISP, well, we've got all the different community lists defined up here. Community lists are defined there. And then we have a route map that basically matches the community and sets a local preference, and so on through. So there's the match for community 70, match for community 80, set local pref 80, match 90, set local pref 90, and so on. So that's the configuration that matches RFC 1998. Some people actually use this RFC. I mean, we certainly did when it was published. We thought, wow, you know, Internet MCI do this, we may as well do it. You know, there was kind of encouragement when it was first introduced for ISPs to try and use the same numbers. And since then, there's been some effort at trying to standardize communities that ISPs use for multi-homing, but it's never really happened. So some people list what they do on the website. Other people will put it into the AS object in the Internet Routing Registry. I've got some examples coming right at the end. So let's have a quick look about some configurations. Let's revisit this example, using communities rather than MED. Got a primary path A to C, backup path B to D. Router E does the aggregation. Okay, it announces the aggregate as though it came from AS 100, as before. I'm either butterfingers, but every presentation I do, I seem to drop this, so it must be something in its shape. We announce the /19 aggregate on each link. Primary path makes a standard announcement. Backup path, well, we don't mess with we don't mess with MED. We actually use a community. When one link fails, the announcement of the 19 aggregate via the other link ensures continued connectivity. That's our backup. Configuration, router A, primary path. Aggregate out, default route in. Nothing new there. Router B, aggregate out, default in, as before. Route map, router D out. This time we're sending community, and this route map actually sets the community on the outbound announcement. Inbound route map, router D in. That is just setting local preference as we did before on the inbound announcement. Okay, so router D out, match IP address prefix list aggregate. So if we send the aggregate out, we set community 100:90. Remember in the early example at the start of the afternoon, we did set metric 90, rather than what we're doing now is set community 100:90. The effect is the same. I mean, metric has got a lot of bad reputation over the years, especially with the metric confusion, which, well, I mean, I'm not talking about here. And so a lot of ISPs don't like using MEDs anymore. And what's taken their place is the community like this. So this is one example of a huge variation of communities that many different ISPs actually offer. And for the upstream ISP, well, this is the main connection, so customer prefix in, default route out. The other link is actually a little bit more complicated now because we've got to have a route map for our customer. The route map basically looks for a community being set on the prefix and adjusts the local preference accordingly. So the next slide has the BGP cust in route map, which matches community 90. We set local preference 90. I've snipped out the other bits because, well, we've seen them before. Okay, so for match community 90, in other words, with C community 100:90 being set on that prefix, we set local preference to 90. So it has the same effect as if the customer set a low MED. But in this case, they're sending a community and we're setting local preference instead. Simple example. There can be more complicated examples, but the advantage is that this scales better and you don't have to worry about MED standards and compliance with the RFC and all the rest. So now let's have a look at some of the service provider communities. Just as the last few slides, here are some working examples. RFC 1998 as an informational RFC is fine. It's fine for simple multi-home customers. The world has moved on a long way since 1994, 1995, when BGP communities were introduced. There's some really, really complicated topologies now. And so the RFC doesn't really handle those complex topologies, or configurations for that matter. So ISPs have come up with their own community policy. And I sometimes wonder about it. I think some ISPs actually compete with each other to come up with the most obfuscated and complex policies around. I mean, everybody knows about the complex Perl competitions that are on the go. Who can write the most complex Perl thing in as few characters as possible? Well, some of the community configurations I've seen must follow with that principle as well. The idea, though, seriously, is to give customers more control over how they can traffic engineer traffic through the upstream ISP's network without having to get the upstream ISP involved. Okay, there are no recommended ISP BGP communities apart from, well, is RFC 1998 a recommendation? Well, it was MCI documenting what they did. There are the 4 standard BGP communities, so you can look at the IANA assignments to find those. No export, what's it? No export, no peer, no advertise, and the Confederation one. Efforts have been made to document all the communities being used. I mean, there was that draft by, I think was it Nicholas Coyton? He did that a long, long time ago, and that's just died. I mean, there was no real interest in that. But it was a survey of BGP communities used. However, these guys here at 1SC, they've done collection of all the communities that I actually, well, most people actually know about, I actually know about, that have been found in the wild. It's actually quite a nice list there. So you can look at all the different ASs and what community policies they've actually publicized. If you know of any more and you want to add to the list, go to the website and let them know. I mean, it's pretty much as the reference that I'm using these days to find out what's going on. So that's a nice service. ISPs usually publish a policy on their websites, so people like Sprint do that. Other people will publish it in the AS object in the Internet Routing Registry. Usually in the RIPE one, because it's most of the European ISPs who seem to do that. If we look at Sprint, I don't know if you can see that at the back, but if you're following the slides on the laptop, you might be able to see it. But I mean, Sprint give you all these options. If you send them these communities, so for example, 65001 something, basically it does a single AS path prepend of 1239 to AS something, where something is this list of ASs that Sprint peers with. Okay? And so on through all those examples. So there are various things that you can do, and you can do different sort of traffic engineering with your AS and your prefixes through Sprint's network. This is an Australian one, AAPT, used to be Connect in Australia. So they've got sort of RFC 1998-like ones. 2764:4, they lower the local preference by 15. This one lowers it by 5. 27642, don't announce outside the local POP. This one is announced to customers and all peers, but not transit providers. Announced to AANX, I really must find out what that is one day. and so forth. They've got these communities. So you can attach these communities to your prefix announcements to Connect if you're a customer, and they will follow the policy that's described there. MCI in Europe. I mean, it's still called MCI in Europe. I just looked up this AS number only a few days ago as I was preparing the slides, and AS702 is still called MCI, so I guess it must be that. And they support these. 702.80, that one familiar? Lower local preference by 80 to 80 with an AS702. But we actually found, and these date back to my day at UNet UK, we also found that we needed to do the reverse of 80. We need to actually set local preference high, so customers could force us to be the primary path. So we also allowed a :120, which set local preference 120. And then the 702.20 only announced to MCI's ASs and customers, 702.30 keep within Europe, 702.1 single prepend, 2 prepend, 3 prepend, and so on. There's a whole heap more. BT Ignite. If you want to see a wonderful list of communities, have a look at BT Ignite's list. This list is actually taken from something that Tiscali did a long, long time ago. They had a massive and wonderful list, and the guy who put it all together was going to write an internet draft. And then he got made redundant and I don't know, I think he got made redundant or left the industry, and well, I've only ever seen them pop up in BT Ignite now. Have a look at this. Just go to whois.ripe.net and have a look up AS5400 and look at the pages and pages that BT Ignite have done. I'd love to see the configuration to do this. But these are all customer communities. I've worked with a customer of BT Ignite and played around with all these communities and had lots of fun, actually. Carrier 1, I've no idea who they are or what they do. But that's probably more because I live and work in Asia rather than being aware of what they're up to. But that's another example of what you can do or what they offer. Level 3, yes. I spoke to some level 3 guys and they're like, yeah, well, this was an interesting exercise, but we're not sure anybody actually uses these. I'm not sure if this is still true anymore, but that's certainly what they have in the AS object in the RIPE database. Again, it's pages and pages of really what I would call bizarre community settings, but that's the sort of thing some ISPs do. You can go to the 1sc.net website and have a look. There are many more ASs listed there and what their community policies are. So if you're looking for inspiration of what to do for communities, for helping your customers multi-home, it's no better place to go and have a look at some of these examples. So as I'm saying here, try and consider using some sort of communities to give policy control to your customers. I mean, if you're fairly bandwidth limited to your upstream connections, you probably don't want your customers playing with your load balancing because you've spent all your time fine-tuning it, and you give your customers these community and they completely break it. So think about it in context of your external links. If you've got plenty of capacity, then give your customers some rope to go and play with. If you don't have plenty of capacity, then you may want to think a little bit harder before you go and do this. Summary. Well, I've done this really, really quickly, but I hope I've shown that multi-homing really isn't that hard. If you keep it simple, keep it stupid, then it'll actually work pretty well. If you try and build in complexity, try and go a little bit crazy with what you're trying to do, then it'll be easier to break, it'll be harder to maintain, and so forth. The other thing I should say at this time is that multi-homing is not a one-time solution. It's not fit and forget. You need to look at this every single week. As I keep saying to ISPs, make it one person's responsibility to be the multi-homing person. And this person, every day he comes into work, maybe, or every week he comes into work on Monday, have a look at the load balancing, see what it looks like. Does it need tuning? If it needs tuning, go tune. Okay? It's never a static thing. I get emails from ISPs that helped many months ago saying, oh, remember that load balancing you set up? It's not working anymore. Well, of course it's not working anymore. The internet changes. You need to go and do things. Oh, how do I do that? Well, I showed you, and so on. So it is a full-time job. You need to look at this once a week. Full routing table is rarely required. Default route is often just as good. If customers really want 200,000 prefixes, it was Sean Duran who said that years and years ago. If they want it, charge them money for it, especially 200,000 prefixes these days. It's not such a light proposition as it was in the early days of the internet. That is it. Hey, I finished 15 minutes before, as I was requested to. Thank you very much. So we've got 15 minutes for questions or 15 minutes to be chased out before the community meeting starts. Or you can just stay here, because the community meeting is going to be in this room at 5 o'clock in 15 minutes. If there's any questions, I'm happy to take them now in public, or you can come up and ask me afterwards. If you want the slides, they should be on the NANOG website. They are. Okay, they're on the NANOG website, so I don't need to put up the URL anymore. Any questions? I'm happy to receive email later on, or I'll be here for most of the rest of the week during the RM meeting as well, so feel free to ask.
Howdy.
Thank you.
So I wonder, earlier you said that some sites are filtering not only with a prefix list, but they're also filtering on AS path, and they do both. I'm using just a prefix list, and it seems to me that if I'm doing that, there's no reason to go ahead and filter on the AS path also. Is there any advantage?
Yeah, I mean, filtering the AS path it appears redundant, but these are the people who are being super safe. The theory is, well, if they blow the prefix list for whatever reason, then at least the AS path filter gives them some kind of protection. That's the theory. There's nothing more to it than that.